when things get to this state, it's often imperative that we repair. We'll use the column on the right, the steel building column, as an example. Again, these elements are only resisting a portion of the loads that they may have to one day. So just because they're up today doesn't mean they will be tomorrow. This particular column needs to be reinforced with some steel plates and things to bring its section back up to what it once was, so that in the future it can resist wind loads and maintain global stability of the building to keep the processes running on the site. So be on the lookout for some corrosion. The removed. We had discussed our lateral X bracing before as typically a lateral resisting element. I'll say that it isn't always the case that it is, but a lot of times when you see these X's in a vertical plane going up your structure, it's part of a lateral force resisting system. Excuse me, in these two photos, we see that we've removed bracing for operational concerns to allow piping to pass through or an access way to be installed. And by removing that bracing, you know, everything's fine from a gravity standpoint. And really, these structures typically don't see a whole lot of lateral load. They're indoors, so not much wind. But what happens if an earthquake hits? By taking that brace out, we've reduced the lateral capacity, the lateral load path, the diameter of our pipe to half at the very minimum of what it once was. And by doing that, we've drastically impaired the structure from a lateral performance standpoint. So consider that when seeing these removed braces, that again, just because it's up today doesn't mean that it will be tomorrow. And these small elements can have large impacts on structural performance in the future. So again, we're carrying on with the removed theme. Over here on the left is some floor grading, and on my site visits with some folks that I work with, I've become known as a bit of a grading stickler, if you will. And the reason for that is I see grading as the first step in that load path between immediate personnel safety and utter problems. You know, that load path begins at the grading and then transfers into the steel beams, over to the columns and down to the foundations. And if that first link in the chain, the grading, is not in good condition and it's not supported properly, you know, we can have some serious problems with personnel safety. So in this picture, you can see the grading has been notched out to allow the pipe to go through, as well as a supporting member. Grading is oftentimes what we call unidirectional. It can only span one way, and those tighter space bars in your grading are your what we call bearing bars. They support the load, and as they support the load, they need something to support them. So with that free edge on those bearing bars there's not a whole lot of load carrying capacity left in that grading, and it could create a potentially dangerous situation. Over on the right, we have another removed brace. This one was taken out to allow access for a walkway, just easier path for personnel to move through, and just kind of an extra example of what we were looking at in the previous slide. So the altered, a lot of times processes change, SOPs change, and we need to figure out a way to do things differently, and sometimes structure needs to be altered to make that happen. In this case, you can see it over here. It's maybe a little bit difficult to see given everything's of similar color in this photo, but this column was added right in the middle of this brace. The brace was spliced, a column was added, and it was put in place so that liners could be pulled out of a mill. And you can see, you know, there's likely not any engineering done on this. The column's already bowed and bending and not adequately sized for what we were doing. So, you know, things like this we should according to that previously discussed MSHA document, have looked at by a competent engineer. So the eroded, here we have some concrete. Concrete's often very good in fluid environments, but certain chemicals will erode the matrix of the paste within the concrete. And it will generally start out with something like we have shown over on the right, where the paste starts to go away, the aggregate's exposed, it gets very bumpy. And if left unchecked, things will progress into a situation that we show on the left, where rebar becomes exposed. And at that point, we may begin to have more problems. So if we catch things early on here and can maybe lay a topping slab on top of that concrete as the aggregate is starting to be exposed, or maybe put a nice topping coat of a good sealing material on top. It might fix any problems, but when we get down to the rebar, we begin to have maybe some serious structural implications. And replacing concrete is extremely difficult. It's usually down near the base of the structure and foundations a lot of times. And you then have to support the structure up above to remediate what could have been fixed very early on with some high quality coatings or a topping slab. So be mindful of these things moving forward. I think this is the last on our list of the good, bad, and the ugly, and this is the cracked. I was told that concrete does two things: it turns hard and it cracks. And a lot of times these cracks in concrete are really not a structural issue. You know, you think about your driveway, your garage slab, things like that. It's probably got a few cracks in it. Nobody's real worried about it. However, there are certain cracks that do create cause for concern, and distinguishing between those two is maybe a little bit more of a technical topic that someone with some expertise should have a look at. Maybe your concrete cracking. Over on the left is an example of the filter support piers that we were looking at previously. You can see a vertical crack running up the left side of the pier, and we started noticing these throughout. You know, this was a consistent thing throughout all the piers, and started asking if we thought there were more. So as we moved forward with the investigations, we tapped, found a hollow noise, and later found the corroded rebar within. Over on the right, this is our same stockpile building. We have damage at the anchorage, and if the steel can't be adequately anchored into the frame, a lot of times our load path is disrupted, and we can have problems. So we will we would recommend some remediation for this likely here in the future. So as we are beginning to wrap things up, I think we've been through the majority of the material that I wanted to share with you today, but I want to leave you with a few takeaways here. One is to perform routine inspections and feel empowered to do these things. Like I said, children can do structural engineering, so why can't we? If with a little bit of common sense and some forethought, we can mitigate problems like that conveyor we saw in the first slide. If you have questions, bring in folks from external sources with maybe a little bit more expertise to help with designing solutions to problems, or even helping identify if problems are even there. I would recommend, however, that you do maybe think about performing routine external inspections from competent folks on some of your maybe higher priority structure, some of your dynamically loaded structure, your cranes, conveyors, and that supporting vibratory equipment. Things that maybe take a little bit more technical expertise to be able to see the problems. And then finally, educate the staff on your sites. We can all do this to some degree, and if you see something, say something. Take a look and report and fix your problems before we have a situation on our hand like the conveyor in the first slide. So with that, I appreciate everyone's time, and thank you for bearing through the technical difficulties at the beginning. And I think I'll open things up here now for questions. My contact information's on this slide, as well as the contact information for Tim White, who helped me develop this presentation and unfortunately couldn't be here today. So if anything comes up afterwards, feel free to reach out. We'd be glad to talk with you.
Okay, if anyone has questions for Chris, you can type those into the chat, and he can answer those for you. Are we seeing anything come in?
I haven't yet.
Okay, well, if like Chris mentioned, if anyone has questions, on the list of attendees, his phone number and his email address are there. Please feel free to reach out and get in touch with him. And thank you very much, Chris.
Yes, thank you, everyone, and have a great rest of the conference.
Thank you. Okay, Nick Tucci is our next speaker. Nick is a senior geochemist with Haley and Aldrich in Butte. He has over 14 years of experience throughout the U.S. related to the use of innovative rapid site characterization and remediation technologies for the prevention and mitigation of mine drainage. He has a master's from the Mine Waste Technology program at Montana Tech. He has co-authored 2 chapters on the monitoring and modeling of acid mine drainage and has published several peer-reviewed journal articles dedicated to the geochemistry, fate and transport, and reclamation of mining impacted sites. So without further ado, I will give you Nick Tucci with Haley and Aldrich.
Good morning, everybody. Could everybody hear me okay?
Oh yeah.
Yes.
Right on. Fantastic. So before I get started, I want to apologize for 2 things really, other than looking a little COVID chic these days. I haven't had a haircut since February, but I'm working out of my home office as a result of COVID. And 2 things are going to happen during this presentation. My neighbor's going to walk his beagle that bays constantly while he walks it, and that sets my new office mates off, and they will be barking during this presentation. And then shortly after that, my mailman is about to arrive, and that will set my dogs off. So you'll be hearing dogs barking in the background, and I apologize for that. I am going to talk to you today about expedited high-resolution site characterization. I know this is the engineering session. I am not an engineer. I speak engineer, but I'm not an engineer. I'm a geochemist. I work on contaminated mine sites, specifically with surplus sites, Superfund sites. I've worked up and down the Clark Fork here from Butte to Missoula. And I can tell you that I've been a part of a number of engineering designs and RDRA activities. And some of them have been amazing. Some of them have been not so amazing and needed further optimization and work. And if you were to root cause the ones that did not work out so well, the reason for that, the root cause for that is likely inadequate characterization. So I'm going to talk to you today about a new type of characterization that's called high resolution site characterization. And I'm just going to dive in here. Oh, I do want to give a shout out to my co-authors. This was a very large project, and my co-workers Murray Einerson, Chuck Payne, and Jacob Chu from Haley and Aldrich had a lot to do with this. And also our client from the Greenfield Environmental Trust, specifically Lars Peterson and Tasha Lewis, had a great deal to do with actually kicking this type of high resolution site characterization off the ground. It's relatively new. There's not a lot of technical guidance on it, and they were very supportive of this approach, and it turned out to be very successful. I'm pretty excited to be talking to you today about it. Brief agenda. I'm going to give a overview of the high resolution site characterization and compare that to the conventional characterization approach, and then I'm going to dive into our case study and then talk about project successes after that. So the conventional approach to subsurface characterization really is akin to throwing darts at a dartboard, only you're blindfolded when you're throwing those darts. You have a site, you know you have a release, and you start to drill. And typically when you first start off, you drill three borings, 3 wells, and you try to triangulate the direction of groundwater flow. That is a 20th century solution, and we have learned a lot in site characterization since this methodology was employed. And really it's antiquated. And the reason why it's antiquated is because you start off drilling a minimal amount of wells, and then you increase it and you continue to increase it until you have adequate characterization of your site. But typically you're under a strict timeline, and this approach does not adequately allow to have project successes in that quick timeline, whereas high resolution site characterization does. high-resolution site characterization is the completion of multiple borings and multiple wells in parallel, located orthogonal or to, sorry, I don't know why my screen keeps on jumping around, or perpendicular to your plume axis. Not only are you installing multiple wells in the lateral direction, but you're installing multiple ports in the vertical direction. So you're characterizing in 3D your not only your source area, but your plume in multiple areas of the plume, starting with the source area, upgrading to the source area, and then downgrading it all the way until you have your plume laterally characterized. The biggest advantage to this approach is that it's scalable. You can scale it from the beginning so that you have a monitoring approach from cradle to grave on your project. And so the typical rule of thumb is you have a source area, you know roughly how the dimensions of your source area. And the rule of thumb is typically you want to install wells and borings along your transect about 1/3 of the size of the dimensions of your source area. So if your source is 600 feet wide, and you know your source is in your area is about 600 feet wide, you want to install your transect on 200, or your wells along the transect on a 200-foot spacing. The site, and I'm going to jump into the case study here. This is actually a picture of the site. This is the site. This was a 3.5 mile long plume, and these are the transects that we installed along that plume. The site is in Soda Springs, Idaho. It was the former Kerr-McGee Soda Springs facility. It was a roughly 550-acre facility that operated a vanadium extraction facility between 1964 and 1999 when it became a Superfund site. And then from 1997 to 2002, it took calcined tailings from a nearby phosphate producer and produced fertilizer from it. So it had a bunch of waste in place. The plant closed in 1990. In the mid to late 1990s, Dames and Moore did a remedial investigation. They determined that the source was from these water management ponds. They closed the ponds. They removed the waste in the bottom of the ponds. They put those into a repository, and they went into post-closure activities, which involved M&A monitoring, and they were monitoring the reduction of site COCs in the groundwater over time. They finished up with the RDRA activities in around 1997, and they were seeing precipitous drops in COCs in groundwater. Predominant site COCs, there are others, but the predominant site COCs are molybdenum and vanadium. And then in around 2000, 2004, those concentrations began to level off in groundwater, so they knew they had a residual source. And then in 2017, EPA released their 4th 5-year review for the site, and requesting that supplemental remedial investigations occurred. They requested and mandated that a supplemental remedial investigation. And so there were certain data gaps that they knew about. They didn't know what the source for dissolved COCs to groundwater would be. They didn't really know off-site COC migration. They didn't have vertical control of their plume. They didn't have lateral control of their plume. They didn't know how far it went. They knew that some COCs were likely naturally occurring, so they weren't sure which ones, or that there were alternative sources. They weren't sure the groundwater velocities. They weren't sure what the natural attenuation processes were, and they wanted to know if in situ, ex situ remedial options were available for the site. And so we designed a field investigation, a supplemental remedial investigation that involved sonic drilling, continuous measurements with XRF, and pretty novel mineralogical analysis to quantify and characterize the source, and then the fate and transport of site COCs. And then tried to differentiate between natural background conditions and alternative sources and our site COCs. And it was a pretty successful approach. But it all involved, and we used over 27 innovative technologies, which included high resolution photography, custom graphical boring logs that were based off of the lithology of the site, continuous XRF measurements to understand source areas. We installed continuous multi-tubing wells, or CMT wells, which I'll get into in a little bit, which allowed for the installation of up to 7 ports with depth with the drilling of 1 borehole. So incredible cost savings for that. But in reality, the success of this project is due to high resolution site characterization. We installed 5 transects. We installed 1 upgradient transect. We installed 2 site transects, 1 here, and then this one right here is just at the down gradient portion of the site known as the FIAB transect, which stands for Former Industrial Area Boundary. And then 3 down gradient transects, all to characterize this plume. It was over 3.5 mile long plume, and it had actually been not characterized up until this point. I don't know if you guys have ever heard of CMT multi-level monitoring wells, but they're pretty nifty. They were developed by my mentor at Haley and Aldrich, and basically it's a continuous tube with up to 7 channels in that tube, and then you custom cut the screens for each of these and install them. And so one well has 7 ports that you can monitor with depth, and those ports are discrete and isolated from the other depths. So you not only get water quality from multiple depths in one hole, but you also get instantaneous head determination, because all you have to do is, when you complete these, is lower down your water level probe. You don't even need to have a survey done, because it's just the difference in head is the difference in the depth of water from one port to the other. So we installed, I think we ended up drilling about 12,000 feet of core. We installed about 54 CMT wells along those transects. And one of the best, I think, advantages to CMT wells is there's just not a lot of purge water, and it's very cheap to sample the water out of these things. This is actually a commercially available check valve pump. It's kind of similar to the pumps that they use in the oil fields. And you use a automated arm at the surface, and what it does is it moves this ball up and down, and it seeds and seals in that portion of the well. The purge volume of these things is about 20 milliliters per foot. And so, you know, very low purge volume, and you could move from you could sample all 7 ports within the matter of 2 or 3 hours. And so the field investigation was relatively comprehensive. We installed 27 borings to sample the residual source area, and then we installed 57 CMT wells along these five transects. And so there was 2 parts to this. There was a solid phase characterization and also the plume characterization. We wanted to know, you know, what the residual source was, can we remove it? And then if we have to do groundwater remedy, where do we have to focus our efforts? And what are these, you know, there was up to 17 potential source areas remaining on the site. What of those source areas, what were the biggest contributing sources to groundwater? So this is a picture of the site, and one of the more interesting aspects of this and innovative aspects of this project, this was actually client driven, is that they wanted to do this in a very short time frame. They wanted to get to a broad modification and final remedy and site closure within a period of 2 years, and that started with site characterization. And we worked with Pioneer Technical Services out of Butte on this. They were responsible for the demolition of existing property, existing infrastructure, the buildings on the site, and also removal of primary sources. But first we had to characterize the sources. And so we designed a very rapid site characterization that was a data-driven process. We had very strict institutional controls and developed a method for rapid changes and approval processes for switching up the field investigation and changing the field investigation based off the data that we were receiving in near real time, so that we would have the site fully characterized, know that there were no data gaps left in the investigation, and then the removal team could come in behind us and do removals based off of that characterization. And so this is what the site looked like prior to removal. This is when we first started the drilling program. We were operating 3 drill rigs to increase the timeline. Here's rig 1, here's rig 2, and then this is what the site looked like a couple months later. They had done the demo, and they had removed the sources that we had identified. One of the things that was more interesting on this project to me as a geochemist is that if you're familiar with neutral rock drainage at mining sites, this site acted very similarly to a neutral rock drainage. It had neutral pH, and you had COCs that you would expect to see at a neutral rock drainage site. You had arsenic, molybdenum, manganese, and vanadium. And I had mentioned before that molybdenum and vanadium were the big players for us as far as it was driving the risk at the site. And fortunately for us, the source area, it was a liquid source, and it had migrated into the subsurface, and it was super saturated with respect to molybdenum and vanadium mineralogy, and they precipitated out really interesting minerals that you could see. And so we were able to visually trace the contamination, find the vertical extent, find the lateral extent, and then follow that up with more mineralogical and laboratory analysis to confirm that we had bound all ends of the plume and the source. And so we set up an on-site mineralogical analysis lab where we were running a field XRD, we were running microscopes, and then we had a dark room. The one molybdenum mineral, powellite, that was controlling the solubility of molybdenum and the fate and transport of molybdenum in the plume lit up like a beautiful blue-green under UV light. So we were running a dark room, and then we were just scanning our core, looking for this mineral to see where it was. And then we would send samples that pegged with this with our on-site mineralogical analysis. We would send them off for further mineral identification at Montana Tech. And Montana Tech has a great mineralogical analysis program. I was significantly aided by Dr. Chris Gammons from the geochemistry and geology department, and Gary Weiss from CAMP, from the metallurgy program. And Gary was running the SEM. And this was one of the ways, I would mention that manganese was a site COC, but we were able to determine actually that manganese was a naturally occurring source based off of the mineralogy that we saw on the site. This is kutnohorite, which is a manganese carbonate, and it was all over the site, including in background areas up gradient of the site. So we knew that manganese was being mobilized under naturally occurring conditions. And so we were able to eliminate that from that COC from the program. One of the biggest advantages of high resolution site characterization is actually that you can map the source in 3D, and we did. And this shows the extent of molybdenum in 3D. And what we were very surprised that we were seeing molybdenum at depths of over 300 feet, and we couldn't understand why until we mapped this thing in 3D. And we're able to see that there are these typical drawdown features in the 3D model that you can see here, and it all related to how the site received its makeup water for its system. There was an old extraction well that was completed at 300 feet below depth, and it was drawing down these plumes down at depth. Once they abandoned that well in 1995, that vertical driving mechanism was no longer available. And so we were able to determine that the more, since removal and since the site was shut down, the current source area was relatively shallow in the upper 50 feet. Another advantages of high resolution site characterization is that you could map your geologic conceptual site model in 3D in very high resolution. And this really did save us, because there was 2 prior supplemental remedial investigations that ended up failing to fill in the data gaps. And it was because the geologic conceptual site model was mischaracterized. We actually identified a graben feature that was located just west of the site, and this graben feature was acting as a very high area for hydraulic conductivity, and it was actually controlling the westward migration of our sites. The plume would enter into this graben feature, and then it would just act as a preferential flow path to the south, and it was controlling the direction of our plume core. Another pretty interesting thing that we coupled with that is XRF technology. We did continuous measurements of XRF for not only site COCs, but 50 other indicator parameters, and we were able to, and this was very beneficial to us, because the site is in the Blackfoot volcanic field in southeast Idaho, and it's a series of quaternary basalt flows with interbedded aeolian deposits in between, and so it's very difficult to actually determine where you are in the stratigraphic column based off visually, because sometimes you're going through these aeolian deposits which you could use to determine which basalt flow you were in, but in other times you didn't miss them. You just completely missed them. And so we were actually able to use zinc and zirconium ratios to determine which of the basalt features we were in. And this QB4 right here acted as the predominant carrier for our plume core. And we were able to trace that all the way to the south and fully delineate our plume based off of these unique parameters and differentiators for us. The site was also controlled by faulting. The faults, there was about 7 faults that ran through our site, and we were able to show that the predominant carrier for our plume was within these fault zones that created these high conductivity lattices, which are outlined in blue here. And so we were able to get incredible control over our plume core dimensions. And we turned that into a fate and transport mass flux model, which we can use to now that removal has occurred, we got a baseline. Moving forward, we can tell exactly what's mobilizing off our site, and we could base the performance of the removal and the remedial decisions off of this model going forward. And for molybdenum, the site is over 3,000 feet long from east to west. And we were able to narrow down the plume cores migrating off site to 2 predominant plume cores where over 95% of the vanadium and molybdenum mass discharge was occurring. We named them AOC 1-2 as areas of concern. We had over 12 areas of concern, and we were able to determine that the source for AOC, this plume core was the result of area of concern 1 and 2. And this plume core was the result of area of concern 3, and then we were able to concentrate remedial efforts based off of what was leaching to groundwater. And this is just a simple block model showing that those plume cores migrating off site. These are those faults, and then you could see the two plume cores. There's this one and there's this one right here. This AOC 1-2. This was mobilizing from where they had the vanadium plant. Extraction plant right here. They were operating a solvent extraction facility right here. That mobilized a bunch of vanadium and molybdenum, and then there was a solvent extraction holding pond that was unlined that contributed over 95% of the molybdenum that was released from the site. and these were our 2 plume cores. And so if we have to do groundwater remedy in the future, we know exactly where we have to do it. And I think, you know, this is one of the last things I have. I'm sorry, am I over time? I'm at 25 minutes. Okay.
You're okay, Nick.
All right. And so this is the vanadium plume migrating south from the site. This is the molybdenum plume migrating off site. The molybdenum plume was over twice as long as the vanadium plume because vanadium attenuates very rapidly in the aquifer. But molybdenum actually, there was only powellite the formation of powellite was controlling the fate and transport of molybdenum going off site. Once these sources were removed, we were able to show that powellite is going to the mobilization of molybdenum is going to be reduced significantly, over 95%, and it is going, and the removal that for vanadium, the same with vanadium, but vanadium is going to attenuate out more rapidly based off of just the retardation factors for vanadium. And so some project successes, I'll go over these really quick. We had, you know, characterization and remediation was conducted in parallel. We fully delineated all site COCs in the solid phase in 3 dimensions. We were able to determine that there were alternative or naturally occurring sources for 3 of the 7 site COCs. We fully delineated site COCs and groundwater in 4 dimensions, including over time. And we recorded the deepest CMT well ever installed, according to Solence, which was over 300 feet deep. And then we successfully tested a redox manipulation remedy, which I'm not talking about this because I only had 25 minutes, but it was able to, we ran a push-pull system, a redox manipulation system where we were able to mobilize, we were able to immobilize molybdenum, vanadium, and groundwater within one of those 2 bloom cores. And so this isn't only about how great we were at this. This is about lessons learned, and there were keys to our project successes. You know, we had, you know, and it all stemmed from a thorough data review and formulation of initial site CSM, which allowed us to generate these working hypotheses that we experimented and actually tested throughout the entire field program. We had this data-driven, real-time data gathering effort that drove our decisions for future field activities. The high resolution site characterization, it was scale appropriate technology, and it was by and large responsible for the successes we saw at this site. We tested various innovative technologies at the beginning of the field program. We actually took the time and did method development, and that paid off in spades. We had a rapid approval process for data-driven changes to the field program. EPA, it was based off of a quick email, and within 24 hours, we had approval for our requests for change, which allowed us to continually develop and refine field procedures. And then we had frequent communications with our client as well as with the regulators. And that's it. Any questions?
So if anyone has any questions for Nick, please feel free to type those out in chat. Any questions?
I guess.
All righty, well, if anyone has questions for Nick at a later time, please feel free to contact him via phone or email, and he will get back in touch with you. Thanks a lot, Nick. I appreciate it.
You bet. I'm trying to stop sharing, but I can't find my window. I'm searching frantically for my window, for my Teams window. So you're going to have to share over me, I think.
Okay. So while we're waiting for Nick to get off on his end, okay. So our next presenter is Terry Beer, and Terry is an environmental engineer with a master's from Montana Tech, where she studied water treatment options for mine closure. She is a Butte, Montana native and now lives in Bozeman, where she is a senior environmental engineer with Enviromin Incorporated. At Enviromin, she mainly focuses on biological mine water management and permitting efforts. And just a little side note, I do think maybe on the list of attendees, I listed Terry's, I had a typo on her affiliation, but Terry is with Enviromin. So thank you very much, and I will turn it over to Terry.
Thank you, Susie. I hope everybody can hear me well. I'm experiencing an unplanned power outage at my house, so I'm running this off a hotspot on my phone.
I can hear you fine.
Okay, great. It seems to be working so far, but please let me know if there's any issues. So like Susie said, my name is Terry Beery, and I'm going to talk to you today about the use of biocoupons for monitoring and full-scale biological water treatment systems. Before we get started, I would like to acknowledge Dr. Lisa Kirk, Enviromin's principal biogeochemist, Dr. Seth D'Imperio, our principal microbiologist, and Dr. Brent Payton of MSU for their years of work on this topic. They started doing research in this arena years ago, and I've only just recently been brought into the fold within the last few years. So thanks, you guys. Okay, so to kick us off, we've all heard so much about passive treatment of all industrial waste, and we've heard a lot about how they're not always understood and that they do not always function well. But today, I'd like to talk about successful in situ water treatment systems that stem from identifying which microbes are present in a system, what they are capable of doing, and what they are doing. If we know these details, we can find ways to stimulate the reaction that we want. And if we know exactly what we are looking for from the get-go, we can start to incorporate this knowledge on the front end. So it is common practice to typically rely on microbes during the soil waste and remediation phase. But we also know that we can use them in water treatment, and we can start to incorporate our understanding of these organisms into process engineering, biooxidation, hydrometallurgy, our facility design and models, and in situ source control, and initially waste characterization. So if we start designing our systems, starting with waste characterization with microbes in mind, and with the end goal in mind, we're going to be a lot better off in the long run. So biological water treatment relies on microbial activity that occurs in biofilms. In saturated systems, these biofilms co-occur with planktonic communities. The relative abundance, diversity, and metabolic activity of planktonic organisms differ from attached biofilm. Attached biofilm communities and water treatment systems are understood to be more diverse and more robust than associated detached planktonic communities. However, it can be problematic to sample in situ biofilm. So to demonstrate the difference between biofilms and planktonic communities, we're going to take a quick look at the schematic. So here we are looking at water moving in a pore space between run-of-mine rock and a molecule of selenium and pyrite and gypsum. These green blobs are facultative bacteria that can handle oxygen but are also okay without it. These blue blobs are the anaerobic bacteria that are protected from the oxygen because they're buried in this biofilm. We also have these little orange floating planktonic bacteria that are just free floating in this pore space. So what I'm trying to show here is that it's important to understand this mixed community and how dynamic the situation is inside every pore space. So as we can see here, the selenium, nitrogen, and iron species change as we go from microaerophilic environments to anoxic environments. So how do we find out who is home in these established or proposed systems? Environment does this by microbial community characterization. So this typically starts with field sampling, such as drilling. There's various other methods though. We then process and preserve samples. We take great care during this phase to not contaminate any of these samples with our human microbiome. We typically sample under nitrogen. Various techniques like that are employed here. We then extract the genomic DNA. We amplify the target DNA, and then we send that DNA off to sequencing at a core facility. Once we receive that data back, we clean up and analyze this data, where we run the sequencing through multiple in-house databases to produce a community characterization at the end. So this can sometimes lead to expensive sample collection. As we all know, drill rigs aren't cheap, and they require a crew of people. And if you're also needing to get microbiology samples while you're there, that's additional people. So this can add up, it can be expensive. So Environment needed a way to obtain representative samples for measurement of this microbial community in situ without disrupting the system and without expensive drilling all the time. So Environment does this by utilizing biocoupon technology for monitoring of the attached biofilm communities in situ. Biocoupons contain field relevant materials such as waste rock and are installed within wastewater treatment facilities. Biocoupons are placed strategically to obtain representative samples and left to allow for native biofilm growth over time. Microbial community structure and inferred function is based on DNA and RNA analysis. Changes in this microbial community with time and operational conditions inform the understanding of the treatment facility. And then routine use of these biocoupons informs operational decisions to achieve robust, resilient, and efficient treatment. So you're all probably wondering what a biocoupon looks like and what it is. So biocoupons can be various shapes and sizes. This is an example of one of the types of biocoupons that Environment uses. This one is a perforated stainless steel sleeve that is filled with autoclaved, sterilized composite waste rock collected from drilling at that specific site. So with the drilling of one well, you could obtain enough. Oops, sorry, did I miss somebody? Okay, so with the drilling of one well, you could obtain enough material to fill hundreds of these little containers with waste rock. So it's really efficient strategy for obtaining a lot of material at once and being able to carry out the study for a long period of time. As you can see, this biocoupon is not very big. It's maybe 4 inches long by 1/2 inch to 1 inch in diameter. So typically these biocoupons are attached to stainless steel cables for deployment in wells, adits, ponds, pretty much any water treatment scenario you can think of, this would be applicable for. So now I want to get into how this is relevant at the field scale. This is a saturated waste rock fill used to treat nitrate and selenium at a North American mine site. Multiple wells are used to inject, monitor, and extract water. So water, carbon, and nutrient amendments are injected over here at the right, and water flows through along these red lines indicating a flow path, where it is extracted over here at pumping wells and left placed in a pond before discharged to down gradient water. So again, water is injected over here with nutrients and carbon, flows this direction, is extracted over here, and then placed in a pond so that chemistry can be performed before it is released down gradient. These little blue dots in the middle here represent monitoring wells, where we can install biocoupons, we can monitor chemistry, various things like that. So this highly effective in situ treatment strategy relies on native microbes to biogeochemically reduce nitrate and selenium by as much as 98%. This recently demonstrated technology is being transferred to commercial use and is thus necessary to understand how microbes affect that water quality. So, who's home, what are they capable of, and what are they doing? Those are our 3 main questions. This information is imperative so that we can optimize the system and resolve any upsets in performance. So these biocoupons were placed at various steps within this well field and collected periodically to represent operational changes. So we can see here we have a water level. We placed a coupon pretty shallow beneath the water level. Placed the next one a little bit deeper at a medium level, and then we placed some at the deepest point in the wells. So this allows us to get a solid look at the distribution of the microbial community across the entire well field and over time. So what do we do to collect this sample and maintain its integrity? Environment uses aseptic techniques to collect the samples, and we immediately preserve them to stabilize the nucleic acids at the time of collection. Once they're at our lab in Bozeman, we detach these biofilms from the rock surfaces using a process designed for low-yield subsurface systems. We collect that biomass and then proceed to extract the nucleic acids. These samples are then sent to core sequencing facilities for sequencing of bacteria, archaea, and eukaryotic organisms. We can also evaluate gene expression using qRT-PCR in our lab. These genomic results are then analyzed using our customized data pipelines to identify the microorganisms, their relative abundance, and probable function. And we can also use qRT-PCR to evaluate absolute abundance. So for example, we might identify a group of nitrate-reducing microbes and infer that they are reducing nitrate in our reactor. We can use qRT-PCR to show that nitrate reductase enzymes are being expressed and to quantify the number of actual nitrate-reducing microbes present in the system. So what are some ways that we can use this data to evaluate what's going on in our reactor? We can look at one specific area in the system as shown in this chart. The data in this chart is lumped by inferred function. So we can see that denitrifiers make up about 17% of the microbial population, which is good if you're trying to remove nitrate from mine-affected water. But it is also important to recognize that the microbes that we rely on for denitrification are only a part of the ecosystem that affects water treatment. We have hydrocarbon degraders over here, we have iron reducers, we have iron oxidizers, and we even have undefined metabolisms that we just haven't been able to put our finger on what they do yet. Can also look at microbial community in different ways. In this figure, we're looking at relative abundance on the y-axis over here, while differing types of wells are shown on the x-axis. If you remember, I mentioned the injection wells, the shallow, medium, and deep wells, and those pumping wells. The legend identifies which types of organisms are present by color. So the blue are the denitrifiers, orange selenium reducers, gray iron reducers, and the yellow the sulfur reducers. We can see that there is a large abundance of sulfate-reducing bacteria present at the injection well. This is due to the high availability of carbon that drives oxygen availability to a very low level. This is useful information for operators as they can be aware of any potential sulfide risk and make necessary adjustments. So we're using the microbial community here to inform operational decisions. As water moves through this flow field, through the shallow, medium, deep, and out the pumping wells, we can see that we have very similar relative abundance across multiple organism types. We can also see that we have denitrifiers, selenium, iron, and sulfur-reducing bacteria, but there's not a lot of variance by depth. This information is evidence of the in situ microbial community supporting denitrification and selenium reduction with some local iron and sulfur reduction. This might also suggest that the system is slightly overfed, which gives us more operational information to utilize while optimizing the system. We can also use biocoupons to compare differing well types with time in reference to the microbial community. Here we are looking at denitrifiers with percent relative abundance again on the y-axis and differing well types on the x-axis. The legend indicates time steps from 0 to 9 months. We see that there wasn't a lot of growth initially at the injection wells, but around 4 months, we see an increase in growth. We did not obtain data for the 6-month time step, but we see this trend continue at the 9-month time step. The abundance of denitrifiers increased over time in the monitoring rows, with a max at about 4 months, decreasing around 9 months. At monitoring well 8, we actually had a methanol spill occur, which caused this great big spike at 4 months in denitrifiers. This has since leveled off around the 6 to 9 month period. In the pumping wells, we see a lesser % relative abundance, which suggests that most of the treatment happens upstream in the reactor. So by the time the water gets to the pumping wells, most of the denitrification has already occurred. So you can see that this data allows us to track how the community is responding to treatment strategies and environmental stresses. On the previous slide, I had mentioned a methanol spill. We're going to dive into that further here. So in this figure, we are measuring relative abundance of iron reducers on the left and sulfate reducers on the right. Again, the y-axis is relative abundance with differing well types on the x-axis. The legend indicates 0 to 6 months for the iron reducing graph and 0 to 9 months for the sulfate reducing graph. If you look at MW8, where I had mentioned there was a spill, we see a spike in iron and sulfate reducers around the 4-month time step. So we can infer that in this system, excess carbon leads to an increase in iron and sulfur reducing bacteria. So the importance of who's home, which is one of our key questions. It's the key question. The understanding of the microbial community helps to shape key operational parameters, including the growth substrate that we need for microbes to provoke the needed response, to identify and amend for any nutrient deficiencies, so that we can understand the resilience of this community in response to treatment stresses, such as oxygen, feed rate or influent chemistry changes, changes in flow due to plugging, biofouling, or operational responses such as changes in carbon dose or delivery or nutrients. So with that, what are some other biocoupon monitoring possibilities? Microbial community monitoring is possible in almost any setting. As you saw in that picture, a little stainless steel perforated sleeve can go in pretty much any water treatment scenario you can think of. They're applicable basically anywhere, and they can be various shapes and sizes. So Environment is currently using them extensively in saturated rock fills and in flooded underground workings. But what about unsaturated rock fills or sulfate reducing trenches, process plants, or at abandoned mine reclamation? In these pictures depicted here, we have the top of a wellhead. And in this picture to the right, we have the bottom of the well where it's completed in an underground adit that is not yet filled up with water. Since this time, this adit is full with water, and we do have a biocoupon hanging in this well so that we can track changes in chemistry and microbial community with time as this adit fills up and is closed, which will hopefully help inform abandoned mine reclamation at other sites, not only this one. So with that, I'd like to thank you all for attending my talk, and I'd like to acknowledge our team in Environment one more time. We are a multidisciplinary team where none of us are experts in all subjects. So we work closely together and rely on each other's collective knowledge daily. Does anybody have any questions? And feel free to shoot me questions later too, or set up a meeting. If I don't know the answer, one of our team members at Environment surely will, and we'd be happy to get back to you.
Okay, any questions for Terry? So we are at break right now. We are scheduled for a half-hour break. Actually, we're just slightly ahead of schedule right now. So we're actually scheduled to come back on at 11. So we will go to break. And when we come back, we will resume with a presentation from Dan Bonner. So we will See you soon. Thanks.
Thanks, everyone.
Okay, Terry's got a question.
Oh, Terry, you have a question?
How long does the DNA analysis take?
The question is, how long does the DNA analysis technically take?
Great question. And I will try and type this response in here too, for the
Okay.
record. But it usually, once we get samples back at our lab, it can take anywhere from a couple weeks to about a month to extract the DNA, amplify the DNA, really feel confident that we have a good sample before we send it to a sequencing facility. Once there, we usually get results back within a month. So from collection to getting results back, it's usually a 2-month process.
Great. Anyone else?
How much does the typical biotesting suite cost per coupon?
Another question, how much does the typical
Biotesting suite
biotesting suite cost per coupon?
So that's also a great question. And it does vary. So I'll try and be kind of nebulous here, but answer your question. So for every coupon, it really depends on how much microbial activity is happening at that site. If you have a site where a lot is going on and we have a lot of microorganisms attached to that coupon readily, and there's a lot of biomass available, it doesn't take much effort to extract those nucleic acids in our lab and send them off to sequencing. The actual sequencing is relatively cheap. It's less than $100 a sample, typically. But the tricky part is if we're placing coupons in a system where there's low microbial activity, it might be a little bit more tricky to extract those nucleic acids and hence take more of our time. So that's kind of where some of the costs can add up there, is the actual extraction before sending to a core facility. But it's not very expensive process altogether. Less expensive than like a metals test typically.
Any additional questions for Terry?
Thank you guys. I appreciate you taking the time. Have a great rest of the conference.
Thank you, Terry.
Yeah, now you want.
Okay, so we will now go to break. We will be back at 11 a.m. Thank you. phone numbers and email addresses that were provided on the list of contacts. So if you have questions or to set up some side meetings to continue that networking opportunity for the conference. So, alrighty. Our next presenter is Dan Bonner with Arcadis. Dan is a technical expert, account manager, and mining service leader for Arcadis, and brings more than 20 years of experience as a professional civil engineer, consulting on large-scale mining, water resource, and heavy civil construction projects. In addition to solving complex technical challenges, Dan enjoys the challenge of working with multiple and diverse groups of stakeholders and helping to work towards mutually agreeable solutions. Increasingly, given the environmental challenges we face, Dan also strives to incorporate sustainable practices and design features into his work. Welcome, Dan.
Okay, thank you very much. My audio coming through okay?
Yes, you sound good.
Great, and you can see my screen.
Yes.
Perfect. Thanks very much for the introduction. Yeah, I'm Dan Bonner with Arcadis, and I'm going to be sharing with you today about pit lake treatment at the reclaimed former Farley mine. It's a project that Arcadis has been involved with for a number of years. Continues to be a very interesting project. Before I launch in, I just wanted to extend a huge thank you to Susie Anderson and the rest of the Montana Tech team. I'm sure it's been a monumental task converting this conference into a virtual setting, and I'm sure there's been a ton of stressors, especially this morning with the change up on YouTube. So just thank you to Susie and the rest of the team. You guys are doing a great job and really appreciate you setting this up. Of course, I'd rather be in Montana right now at the resort, but Reno, Nevada is not too bad. So there was a number of folks who worked on this project. I honestly was on the periphery. I know a lot about this project. The real technical folks who led this project were John Forbert with Arcadis and John Bogan. We also had Cole Leask with Arcadis, Wayne Nixdorf with Mine Waste Management, and Omar Barar and Ray Frost with Manitoba Growth Enterprise and Trade Resource Development. I also just encourage you, if you have questions as we're going along here, don't hesitate just to pop them in chat. I've got it right in front of me. So if you have any questions, no need to wait till the end. We can just talk about them as they come up. Whoop. First glitch. How do I advance my slides? There we go. Okay. So a little background about this site. This was a copper, zinc, and nickel mine near Lynn Lake, Manitoba in Canada. So you can see I dropped a little pin here. I'm pretty far up north. Well, north if you're from the US. This mine operated from the 1950s through about 1976. And during the course of operations, generated about 20 million tons of acid generating tailings and waste rock. Those tailings and waste rock were stored at the surface, and the operator constructed a series of impoundments to collect the ARD runoff, capture it and treat it, and then release. The site was also seeing, despite that treatment effort, the site was seeing impacts due to surface water, or in the surface water, the adjacent river, and just sort of the surrounding areas due to this ARD material. They were also seeing impacts from windblown dust from the tailings impoundment. And their treatment for the ARD consisted of a manual operation, which I'll talk about here in a little bit, adding lime into the solution to drive the pH up, settle out the metals and the ions. That settling occurred in a dedicated settling pond, which then flowed into a polishing pond. This treatment could only happen in the summer months. As you might imagine, in this part of the world in the winter, it's frozen, so difficult to do anything up there. And their approach really didn't have an end goal. It was treatment in perpetuity, which the operator wanted to look into ways of improving that situation. Talk a little bit about the site layout now to give you the lay of the land here. This is an aerial of the site. And we'll start in the tailings basin, which is this area here. We've got the coarse fraction kind of on the west side, migrating into fines, and then finally the slimes down at the lower end of the impoundment. Here we've got 3 ponds, which they were using to capture what they could from the ARD runoff and impound that solution. One of those ponds was a former pit. They just allowed it to fill up and used it to capture water. The treatment, as I mentioned, was a manual application of lime hydrate. The lime hydrate was added here. It's kind of hard to see, but there's a little facility right there. And you can see as that reaction was happening, you can see the change in water color as the precipitates formed and eventually made its way to the polishing pond where the water was tested and subsequently released as long as it met the treatment criteria or the discharge criteria. There were 3 major pathways for surface water, west, center, and east. You can see the west one was pretty well captured as it flowed through the ARD impoundments. The center is actually 2 pathways, just sort of flowed off to the south in some drainage features. And then the east pathway, again, just sort of flowed off site, wasn't captured, and that was an issue. So when Arcadis got involved, one of our initial steps was to develop a conceptual site model, as you typically do with these types of sites, to identify areas where the bulk of the acid was generated. So we went to each of these drainages and sampled and evaluated what we saw running off the site. The conceptual model is as follows. And again, if you have any questions, please type them in. It's difficult to read a crowd when I'm just staring into a camera. So if you got any questions or critique, just lay it on me. I'm ready to answer. So the CSM, the conceptual site model, was that we were having run-on from the north. The way the site was graded, it was coming in from the north. We had run-on and then runoff from the coarse tailings down into the ARD impoundments, as well as just sort of off-site, if you remember those off-site drainage channels or pathways. We were also, the model incorporated evidence of erosion on the fines and slimes portion of the tailings impoundment. We also modeled infiltration, particularly in the coarse fines where the water had a pretty easy time of just, if it got on the surface, just percolate through and express itself out at the down gradient side. We also modeled subsurface flow through the tailings, again, primarily through the coarse tailings. And we observed and incorporated into the model that the bulk of the ARD was coming from the coarse tailings. All of this is acid generating. All of these tailings are acid generating, but what we saw is that the coarse was really the main contributor because water could get in there, react, oxygen can get in there, and the solution that came out either on the surface or in the ground or in the groundwater was low pH. In the fines and slimes, we didn't actually see as much ARD generation, primarily due, it was tighter and oxygen couldn't really get down in there to drive a reaction. So we only ever really saw ARD generation if there was disturbance, either by erosion or human activity. And then again, the pathway of water from the ARD impoundments was through the settling pond, the polishing pond, through some drainage features. Ultimately, it loops around. You can't see it on this slide, but loops around down to the south, comes back up to the north in this water body here. So using our conceptual site model as a guide, we sat back and developed a reclamation and remediation approach. We incorporated 5 key tenets to drive that approach. The first, and I'll show you graphically what this looks like, but the first was to keep clean water clean. Second was to consolidate all the acid generating materials that we could. Third was to minimize the percolation of water into acid generating materials and prevent oxygen from getting into the acid generating materials. Number 4 was to minimize erosion of tailings, fines, and slimes. Again, as long as they weren't disturbed, they weren't really a contributor. And then the last one, which I'll spend some time on at the end here, was to develop a long-term, cost-effective, and sustainable method to manage the impacted water that did come off the site. So to deal with that first tenet, keeping clean water clean, we just built a simple diversion at the top end of the site and prevented that run-on from ever hitting the site. Pretty straightforward. We then restored those natural drainage ways to get better flow off the site. They were, neglected, let's just say, and didn't flow as well as they could be. So we restored those back to pre-mining conditions. We then picked up all the ARD that had made its way out of the tailings impoundment and placed it back into the coarse tailings area. Again, just to consolidate all the ARD acid generating material into one site or one spot. And then we built an impermeable cover, HDPE liner, again, to prevent water from being able to percolate in and limit oxygen a little bit from getting in there, but pretty much cutting off that reaction mechanism. We used about 170 acres of HDPE liner to build that. And then in the fines and the slimes, we just put a semi-permeable cover of borrow material, primarily just to prevent erosion and further surface destruction, but also to limit wind erosion, wind-blown deposits from making their way off-site. And that was about a 240-acre area that we constructed that on. And yeah, so that was the sort of the dirt moving and sort of civil activities that we did to help the situation at the site. And the final step for this overall approach was in our water treatment. Yeah, so other items is post-completion monitoring, continued water treatment. Okay, so now I'm going to talk about the water treatment. Any questions up till now on what we did from a sort of a civil aspect or anything I've said that isn't clear? Give people a second to type because I know it's hard to type on the fly sometimes. Okay, we'll keep going. So I think, as I mentioned, the historical method of treating water at this site consisted of one operator manually adding lime hydrate to the outlet pipe of the reclaim pond. So reclaim pond is here. It was allowed to drain out into this, it's hard to see, but there's a little finger channel there. So an operator literally sat there 10 hours a day with carrying 100-pound bags of lime and sprinkling it into the discharge of that reclaim pond. So I'll let that sink in for a second because I think this is one of the more amazing facts of this presentation. So for a full summer, one person job for 10 hours a day was to carry 100-pound bags of lime and just sort of dump it into the discharge end of a pipe. sounds like a brutal job. If anyone has a more brutal job that they've done, please type it into the chat, because I have yet to hear of one that's as monotonous and as strenuous as that sounds. Not a knock on whoever the operator was. It's heroic that they did that for as long as they did. But one of the questions we asked was, how can we automate this? How can we bring some automations and make this water treatment process a little more automated, safer? And so what we did is installed a water treatment plant there that was essentially, it was intended to be an interim solution built up of modular equipment. We designed it to handle flows between 500 and 1500 GPM. The treatment system consisted of pumps to convey water from the ponds into a reactor vessel, which in this case was a 20,000 gallon frac tank. And it was sized sufficiently to provide 10 minutes of contact time. We had a lime silo installed, so we got rid of the 100-pound sacks of lime and went to bulk. We had a lime silo and a slaker where we could age, mix water and lime together, blend them into a slurry, let them age, and subsequently that solution was added to the reactor vessel. And the whole purpose of this, again, was to drive pH up, which would allow for precipitation of nickel and zinc and some other associated metals. This system went operational in May 2010, just after the spring thaw. So this is now already 10 years ago. We're still involved with the site and still working with water treatment, which I'll touch on here in a bit. So some of the stats, at the start of 2010, we treated 280 million gallons of ARD solution. We built a water treatment plant. And I should say that that manual operation worked to an extent, but we felt it probably led to a lot of unreacted lime. Wasn't great mixing going on in this area, so we think a lot of the lime just kind of settled out into sludge at the bottom of the settling pond. Okay, go to the next slide. Again, so in 2010, sorry, we treated 150 million gallons of ARD solution. We used 600 tons of quicklime, got much better reaction, and quickly filled up the settling pond with treated solids. We installed this sediment curtain, or turbidity curtain, just to keep these sediments from going out into the polishing pond. We operated 150 days, and at the end of that, started planning for the 2011 season. We really looked at our geochem model to predict the effects of what could happen if we tried different approaches. One of the things we started looking at hard was the sludge that was in the settling pond, which we knew there was a lot of unreacted lime in there and metal hydroxides. We started looking at what would happen if we took that, dredged it out, and put it into the reclaim pond. I'll talk a little bit about that. What we did in 2011, so in 2010, we were treating water from the reclaim pond, discharging it, letting it go. 2011, we changed things up a bit. We started a closed system where we pumped out of the reclaim pond, treated up on the shore, and then discharged back into the reclaim pond. So totally closed loop, nothing left the system, let's call it. Our goal that year was to try to pump down the North and Sherritt ponds and get everything into the reclaim pond. Again, with the water treatment, we were trying to increase pH and continue to get the metal ions to settle out, which improved the pH of the water ultimately. Again, during this 2011, we dredged material out of the reclaim pond, or sorry, the settling pond, and put it back into the reclaim pond. And the results were interesting. While this dredging was going on, again, dredging from settling, putting it back into the reclaim, we had our water treatment plant set up, which was pulling water out of the reclaim pond, adding lime, and then putting it back into the reclaimed pond. We monitored pH at the intake of the water treatment plant, which was about 20 feet below the surface of the pond. We also had 3 monitoring locations to monitor pH at the surface of the pond. And what we saw is pretty good, struggling for the word here, but the pH at the 3 surface locations and the intake were pretty much in lockstep, which was a little bit of a surprise because we had thought as we were dumping in the sludge and all that unreacted lime from the settling pond, we thought we'd see spikes of really high pH due to the addition of the lime in some areas and then sort of unreacted zones in the other areas. And we thought this would sort of be like little mini reactions going on in the pond. What really happened is that sludge took a while for once we put it in, it took a little while for the lime and the metal hydroxides to actually dissolve into the pond. That attenuation allowed for pretty good mixing and uniformity across the pond. We didn't do any active mixing. This was all just natural turnover. The lake apparently turned over about once a month. But it was a surprise to see that pH at the surface on those 3 points, as well as in the intake, were fairly uniform throughout this treatment process. Okay. Any questions on this slide? Pick up the pace a little bit. Okay, so we looked at the analytical data for the pond, and we saw that we were achieving excellent metals removal during the dredging program. You can see here we have zinc, nickel, and copper. You can see the relative concentrations before dredging and then after dredging, after we added in that unreacted lime and the metal hydroxides. We saw a substantial reduction in concentration. Same with our arsenic, lead, and silver. And again, you can see the pH during that dredging activity increased due to the addition of the sludge and the ongoing water treatment that we were doing. Okay, so in 2012 and 2013, we just kept doing what we were doing. We treated water from the reclaimed pond, treated it in the reactor, and then put that water, that treated water, back into the pond and just kept it as a closed loop. And our objective at this point was just to continue to maintain enough freeboard in the reclaimed pond to handle the annual inflow of ARD solution. We did not see any reduction in the acidity constituents in the impoundments. In 2013, we installed a swale just to basically hydraulically connect all these ponds to get all the water into the reclaimed pond. And then once we got the water out of the north pond, we actually excavated another 30,000 cubic meters of tailings from this pond that had settled out over the years and placed it into the reclaimed pond. So you can see over the years, we've been slowly excavating, dredging, and getting everything to go into the reclaimed pond as our primary treatment vessel, you can think of it as. We did see a slight uptick in demand of the lime that we're using for treatment once we put the tailings in, which was not unexpected, but notable. So then in the following 4 years, 2014 through 2018, really no water treatment was needed. We had sufficient freeboard created in this pond to last for those years. We could just step back and let that pond fill up. We knew whenever we wanted, we could go back in and start treating the water. We had a proven out treatment program, so we just didn't have to do any work, which was great when you compare that to, again, what they were doing before, which was manual application of lime every year in perpetuity. In 2018, we did have to treat just to, again, to create freeboard. So we used about 493 tons of lime, treated about 124 million gallons of water. And at this point, we're discharging through the old settling and polishing ponds. So all of this was to get rid of the water and create freeboard for subsequent years. So in summary of to summarize our water treatment, since this reclamation and remediation was completed, we've reduced the volume and loading of ARD to the impoundments. So back at the top of the slide or this presentation, I talked about those covers we put on, the consolidation of acid generating materials. That all led to much less ARD solution getting to the impoundments in the first place. We saw great success with putting the dredged sludge back into the reclaim pond. We were able to use that untreated lime and to our benefit. We also saw that the sludge blanket in the reclaim pond that settled to the bottom actually helped mitigate additional acid generation by precluding oxygen from getting in there. And we've set ourselves up and set the client up for a 3 to 4 year gap between water treatment campaigns. When we do discharge, when we are treating water, we're in 100% compliance with our discharge license. So in summary, our model included keeping clean water clean, consolidate acid generating materials, prevent percolation through the acid generating materials. We mitigated erosion and dust generation and neutralized stored acidity. One of the key takeaways, which is really interesting for other sites, and if you've got a site that has been sort of historically treating water with lime, this might be of interest to you. We saw really good beneficial reuse of that untreated lime that was in the sludge of the settling pond. And then we did reduce, we basically, again, set things up to only have to treat every 3 to 4 years. In fact, I think next year we're going to go back out and treat. And we've handed over sole responsibility for O&M to the province, which is where this mine resides. So thank you very much again. I appreciate your attention. I'll take any questions you have now, or you can always email me or call me at the information on the slide.
Any questions for Dan? Oh, yes.
Sure.
No, wait.
Great job. Thanks for discussing your project.
Oh, yeah. Okay. Yeah. We had a comment come through from Joshua Hudgens. Great job. Thanks for discussing your project with us.
I thought my colleagues were going to just heckle me. I'm surprised they didn't give me any tough questions.
I know, you lucked out, Dan.
Well, thanks very much.
Thank you. I appreciate it. Okay, so next up, we have John Witt. Jonathan Witt is a senior environmental engineering manager for the J.R. Simplot Company in Boise, Idaho. He has more than 20 years of environmental engineering experience and currently manages water and wastewater projects and permitting for Simplot. He is a professional engineer and project management professional, and John has a master's degree in environmental engineering. So, welcome aboard, John.
All right, let me see if I can get my screen shared. All right. Okay, can everybody see that?
Yes.
All right. Thank you. So the topic of my presentation today is the physiobiological removal of selenium from mining impacted waters. As I said, I'm Jonathan Witt. I've been the project lead on this project. I'd also like to recognize Alan Prouty, who's our Vice President of Environmental Affairs, and Del Cunningham, who is the plant supervisor there at the mine, as well as Jeremy Albaugh with Brown and Caldwell, who's been our owner's engineer on this project. So first, a little bit of background on what Simplot does. We are a privately held company located out of Boise, Idaho, but we have major operations throughout the world, throughout the US, Australia, Mexico, Canada, China, and in Latin America. Some of the things that we do a lot of things as a company. Some things that you may be familiar with, we pioneered the production and distribution of the first commercial frozen French fries. So if you've gone to a fast food restaurant and bought French fries, you've more than likely bought some of our product there. That is a main core of our business. We are also the largest beef cattle producer in the Western US. And then we also are one of the largest phosphate fertilizer mining and manufacturing companies in North America. So as you can see, we're really a vertically integrated company. The way I like to explain it is we do everything from dirt to the dinner table. And so that makes, I guess, working for Simplot an exciting and diverse job. I really enjoy it. So the location that I'm going to be talking about today is located at one of our phosphate fertilizer mines, or our phosphate ore mines, at the Smoky Canyon mine, which is located in southeast Idaho, right near the Idaho-Wyoming border. The site overview. So you can see in this photo, you can see the mine, some of the reclaimed areas, and some of the active mine up at the top of the photo. And we've got water that's been impacted by historic mining operations and has been impacted by selenium. And some of this water comes to the surface here at the Hoops Spring intakes here down in the lower right, and then again over on the South Fork Sage in springs further to the south. That water is collected right as it comes out of the spring, collected and then piped to a couple of pump stations. You can see the Hoop Spring pump station here in the lower center of the photo. From those pump stations, it's transported to the Hoop Spring Treatability Study Pilot. That's this building with the green roof. There we treat it, remove the selenium, and then it is discharged back out at this outfall. So that's the I guess the really high level overview of what we're doing there. This is a up close, or an aerial photo of the treatment building itself. The first thing that you may notice is this doesn't look a whole lot like a pilot plant. It's an 18,000 square foot metal building. We've got offices, we've got a lab in the building, backup heat, etc. It's a significant pilot, but it is a pilot plant. So as part of, as we were looking and discussing on what we wanted to accomplish through this pilot, there were really four areas that we wanted to accomplish and we wanted to work towards. One was we wanted to remove as much selenium as we could. from the impacted water, with the goal of protecting aquatic life in the stream. And then, because it is a pilot, we wanted to collect as much data as we could to determine really what it could do. We had goals, and I'll discuss those later. We had goals as we started this up, but that was just kind of, those were targets we were working towards. And part of the pilot is determining what this technology really could do. And like I said, I'll go over that a little bit in the future, or in the further slides. But then another thing we wanted to do, and the Dell and his team at the plant, they take a lot of pride in this, is we wanted to be an industry leader. We wanted to do things that really hadn't been done before, and not be afraid to try to push the envelope. And I think we've done that, and been successful there. So the first thing that I want to talk about in detail is the influent water characteristics. We have a very unique mining impacted water. As you can see, we've got a very low nitrate, we've got very low TSS, and low total dissolved solids. Really looking at this water, with the exception of selenium, it looks pretty good. The selenium is primarily selenate as it comes into the plant, and during this data here is from the averages from the first 20 weeks of operation. So some of these numbers have changed a little bit, specifically the total selenium number. That average is a little bit higher now, but this data, everything stays pretty consistent on the influent. Again, we're pretty lucky with the water here. So to go over a very simplified process flow diagram. As I said, we've got 2 sets of springs. Most of the water comes from the Hoop Spring complex, and then a smaller portion comes from the South Fork Sage Creek Springs. Those are pumped to the treatability study pilot, and combined in a wet well there. The plant, the maximum throughput of the plant is 2,000 gallons a minute, and that's the maximum. I'll talk about what the actual is a little bit later, but for these purposes, we'll say that the 2,000 GPM is that maximum. The first thing that we do with that water is we run it through some ultrafiltration units. We've got 3 ultrafiltration skids, and I'll go over each of these unit processes in more detail in a minute. But that ultrafiltration system removes any inorganic or organic small particulates that may impact or plug up the reverse osmosis system. So the ultrafiltration is really there to protect the RO units. But that 2,000 GPM of filtrate from the ultrafiltration is then sent to our reverse osmosis units, where that material is concentrated up. The selenium is concentrated up. So we end up with basically 1,500 GPM of permeate and backwashes, and 500 GPM of concentrated of selenium concentrated water. Then send that to our anaerobic biological reactors. We've got 2 of those, where the selenium is removed, and then the solids from that are backwashed, and that's where the selenium ends up, is in these biosolids. Those selenium-bearing biosolids are then dewatered using a centrifuge and then disposed of off-site. The water coming out of the anaerobic biological reactors, we then need to add oxygen and remove any remaining nitrogen or carbon or anything else that we may have added in there. before we run it, before we send it back to the creek. So we've got activated sludge to help remove carbon and nitrogen, and then these tertiary filtration, some sand filters to help remove any residual phosphorus. Like I said, it's blended back together and then discharged right back to the same creek. So I'll go over each unit process in a little bit more detail, but really showing you photos of it so you can see it. As I said, we've got 3 of these skids, and they're really there to protect the RO units. The reverse osmosis process, we're running at a 75% recovery. So, you know, of the 2,000 gallons a minute coming through this system, 1,500 of it is run through the system and discharges as permeate, and 500 gallons per minute is discharged as concentrate. So for example, if we've got a selenium concentration of 150 parts per billion coming in, the selenium coming out of the RO skids would be about 600. We then move to our anaerobic biological reactors. We've got 2 of these reactors. These are manufactured by Frontier Water, and each of them has a maximum capacity of 250 gallons per minute. So we've got 500 gallons a minute coming in. It splits evenly between these 2 reactors for our 500 gallons of treatment. This is really the heart of the plant, and we have a target selenium recovery goal of 95%. That was set very early on in the project. And I'll go over what we've actually accomplished a little bit later. But these reactors it's a 2-stage process. It's got a granular activated carbon fluidized bed, followed by a granular activated carbon downflow biofilter, where the selenite is converted into a particulate selenium, where it can be filtered out of the water in the downflow biofilter, and then those beds are periodically backwashed. Those solids are backwashed off of the carbon, and then captured and dewatered. So we've been averaging about 640 parts per billion in this water of selenium. Here's another picture of one of the anaerobic bioreactors. In these reactors, we have a number of chemical inputs. We have electron donor, which is a micro C product, basically just a carbon source. We add some macronutrients, some nitrogen and phosphorus in there. And then something that's very important that we add is we add some micronutrients, which are basically just if you want to think of it as a multivitamin for the biology in these reactors. Those micronutrients that we add are cobalt, copper, manganese, molybdenum, nickel, and zinc. And that is proved very valuable and helps the system to run much better when we keep all of those micronutrients in balance. As I said, the non-hazardous selenium-bearing solids are backwashed and dewatered, and that's an important thing to realize and remember, that we've tested these biosolids and we continue to test them, and they're non-hazardous, which simplifies what we can do with them and saves a lot of cost on disposal. As I said, after the anaerobic systems, that 500 gallons a minute travels out to our activated sludge process. these two first tanks in the front are aeration tanks. In back, you can see our covered clarifier. The aerated tanks provide oxygen and internal solids recycle to support the biological community, which can oxidize the materials that can be discharged from that anaerobic process. Coming off of the clarifier, we have a return activated sludge that comes back to the tanks, and then we've got a waste activated sludge that's pulled off of there and then commingled with the solids from the anaerobic process in the building, and then for dewatering. And then, as I said, there's a tertiary filtration process. We've got two continuously backwashing sand filters that we use to remove any residual phosphorus through chemical precipitation and filtration. The sand filter effluent is then combined with the RO permeate, that 1,500 gallons a minute from the beginning of the process, or towards the beginning of the process. It's combined with that and then discharged back to the creek. And then, as I've mentioned a couple times, we then dewater the solids. The solids come in at about 0.5% solids, and we dewater them to approximately 20% solids using a centrifuge. And then they are, the non-hazardous solids are shipped off to a municipal landfill for disposal. So that's really quickly and at a high level the plant, and now I wanted to discuss a little bit about what we've been able to do so far. The plant started up at full operation in December of 2017, so we're coming up on 3 years of operation. As I said before, the maximum forward flow at any time is 2,000 gallons a minute, but when you take out the backwashes and you take out maintenance activities, and this, as you can see, is a pretty remote location. So one of the struggles we've had is with some power outages and some power glitches. When you take those things out, we're averaging about 1,700 GPM of forward flow. Since startup, we've treated over 2.1 billion gallons of impacted water. And this picture here is a picture of the outfall. So you see where we've got the outfall, some large boulders for energy dissipation prior to discharge back to the creek. So now I wanted to discuss a little bit of the effluent characteristics. And this, again, in this table is during the first 20 weeks of operation, but the constituents in the effluent have been pretty consistent, with the exception of the selenium, which I'll show you in the next slide. But we set effluent target concentrations for all of these key parameters, and as you can see, we're well below all of them, with the exception of total phosphorus, and we're just below the effluent target concentration. And the reason it's that way is because we have some control over that. We now have bumped up our ferric chloride dose to our sand filters to precipitate out more of that phosphorus. So that number is lower now, but we've been able to maintain or be below our target concentrations for all of these parameters, with the exception of total selenium. If you look here, we had a target of 7.2 parts per billion. And what that was based off of was just based off of our our initial concentration, which was 144 parts per billion, and just taking 95% of it. So we kind of just set that as a target. You can see during the first 20 weeks, we averaged about 15 parts per billion, which put us right at about 90% instead of 95. But that goes back to one thing I said during our goals is because this had never been done before, we really didn't know what we were going to get. And so we had that target, but really the goal of this was to figure out what we actually could do. And during the first 20 weeks, we're at about 90%. Over these first 2.5 years, we've averaged a little over 85% selenium removal. And we've got a number of projects in place that we're looking at, and one that we're going to start actually going to implement tomorrow to try to bump up and reach that 95% removal goal. But the effluent water characteristics have looked very promising throughout the project. Like I said, selenium removal over the project life has been about 85%. We've removed approximately 2,300 pounds of selenium from the impacted waters. And we're continuing to run. Every day we run is a day longer than anybody else has run a plant like this. So we're kind of we're breaking new ground on this as we try to optimize and just as we keep it running every day. A couple of interesting things. These are weekly samples. The in red is the influent, the red circles. And you can see overall we started around the 140, and right now we're in the mid 160s. So we've in the concentration in our influent water has increased steadily. One of the things, some of that is an increase in the concentration in the springs, and some of that is we've tried to target the highest concentration springs. So there have been some springs that haven't increased, and we've tried to selectively target the highest concentration springs. So that's a little bit of the increase that you see here. Is that selectively targeting things. And then the influent, you can also see it has increased also. One interesting thing here is we've seen a pretty consistent removal percentage of that, between 85 and 90%, regardless of what the influent looks like. So if the influent bumps up, we still get that 85, 90%. So that is interesting. A couple of other things that you see these 3 points here in the middle. During some maintenance activities, we had a contractor in one of the control panels moving some things around, and they crimped the electron donor feed hose that was going to one of those anaerobic digesters, and we didn't catch it right away. And you see what happens when basically we turned off the feed to one of the digesters or reactors for 3 weeks. And so that's what it would look like if we were running at half capacity, basically. The good news is once we identified that, we immediately fixed it, and you see it rebounded very quickly. you also will notice this gap here for about a month and a half. We had some problems early in 2019 with a mechanical failure in our clarifier. And so that took us down for a while as we had to do some repairs on the clarifier. But again, the system came back up and has been running.
Made you a sandwich. I'm going for a walk.
It is running pretty good.
I know, it's okay. It was fine.
So,
I was grumpy.
Okay, so lessons learned. I'll hurry, I'm about out of time. Some lessons learned. One thing that we've done is we conducted small-scale pilots on nearly every unit process before we took it to the full-scale pilot. So we did small-scale pilots on the UF, on the RO, on the anaerobic. We did small-scale pilots on the dewatering. This is Jeremy doing conducting the pilot on the centrifuge before we put the dewatering system in. So those small scale pilots proved invaluable, so that when we went to the full scale, or before we spent the money to go to full scale, and then when we went to full scale and started up, everything started up very smoothly because we had already proved the technology. Sometimes we've learned that our surrogate parameters can sometimes be misleading. If, for example, as we monitor the ORP in the anaerobic reactors, there isn't a whole lot of sensitivity there. And so one thing that we've done that's helped us to monitor that better is we've really been tracking our sulfide concentrations in the anaerobic reactors. And if our sulfide concentrations are where they need to be, then we know that we're reducing. Then early on, I mentioned this earlier, but early on our micronutrient balance was out of whack, and we had a lot of issues and a lot of problems with really sticky biomass formation. We had extracellular polysaccharides, EPS, that would just gum everything up. And as we worked through that, and as we identified this micronutrient imbalance, we were able to dose the micronutrients at the correct levels. The biology became much happier and did not and stopped sticking to everything, and that really hasn't been a problem since we did that. So that was a big learning for us, was getting the micronutrients dialed in. And then overall, the things that we've learned from the pilot so far is that combining the physical, the UF, RO, with the biological, the anaerobic biological, we have recognized a lower cost, a smaller footprint, and better overall selenium removal and uptime compared to some other maybe purely biological systems. With that, I'd like to just acknowledge some of our partners. The U.S. Forest Service is our regulatory agency. RSCI was our general contractor that built the plant. West Tech provided the UF and RO skids. As I said, Jeremy Albaugh with Brown and Caldwell has been our owner's engineer. The anaerobic bioreactors are from Frontier Water Systems, and Stantec was the overall integrator on the design. With that, do we have any questions? If we don't have any now, I've got my email there if you think of something later.
Okay, actually, John, you have several questions.
Nice.
Yeah, okay, so the most recent one that just came in is, are you able to keep operations up to volume and spec during winter season power demand increases treating cold water?
That's an interesting thing. Yes, we operate. The water temperature does not change much at all from due to the seasons because we capture it right as it's coming out of the hill. So yeah, we don't have to heat water at all, and the water temperature we're discharging back to the creek is almost identical to what's coming into the process. So again, we're lucky we don't have to heat the water.
Great. Another question is, have you detected any organoselenium species?
Very, very few. Yes, that is something that we have looked for, that we monitor for is organic selenium species. We have not seen significant increases in them over the influent. One of the well, I'll go a little bit further into that. So one of the things that we noticed is we have a large solid storage tank. In the original design, we would store these solids, and then we'd do a dewatering campaign. You know, we'd dewater once a week. But we as we analyzed for the organic species, we saw some, and so we were trying to figure out where they were coming from, and we sampled before and after that tank, and as we stored them in that tank, the organic species were being generated as they kind of sat there. So something that we did is we no longer store, you know, we dewater that every day, and since we've been dewatering every day, we have not seen those organic species. So that was another example, I guess, of us learning and being able to troubleshoot.
Okay. Another question is, can you reveal a cost per 1,000 gallons or a cost per kilogram of selenium removed? You could answer this later if you need a calculator.
Yeah, I know the total cost.
I want to take a break.
So I know the total cost, and I know maybe if whoever has that question, they could email me and I could discuss it with them.
Could you scroll the screen to the very top?
I'm gonna start the grill soon.
Okay. Yes. So Jim, if you want to email John directly, he can answer that for you.
The total cost of the plant. Sorry, the total cost of the plant was about 25 million.
Okay. What is done with the selenium that is extracted?
So the selenium that is extracted is in the solids that are dewatered, and that is disposed of at a municipal landfill. It's non-hazardous biosolids, and so it's sent to a municipal landfill and disposed of there.
Great. Another question is there a target concentration of selenium that you need to achieve for water quality?
I'm gonna hedge a little bit.
And
because it's a pilot, no, but yes, there is a target in the stream. But the pilot isn't designed to meet that. In the future, that may be something that we have to look at. But because this is a pilot, we are just trying to determine what we can get. And we're close, but we aren't quite there. So we may need to look at things in the future.
Great. Okay, and we'll just do this last question. and then we will move on to the next presentation. This question, it's kind of a multi-part question. A few process questions. What is the pore size of your ultrafiltration system? What are you using for carbon input? And what is the contact time in the bioreactor?
Okay, the pore size on the UF is 0.01 microns. The carbon source is a micro C, I think it's a 4400. So it's a carbohydrate-based carbon source. And I can't remember what the contact time is. It's like
okay.
it's like a half hour. I can't remember what the actual is, but I think it's about a half hour in the anaerobic bioreactors.
All right, great. Well, those were great questions. Thank you very much for everyone who had questions, comments for John. That was a great presentation. Thank you, John.
Thank you.
Okay, so moving on to the next presentation is Steve Dent. Dr. Steve Dent has a BS and an MS in environmental engineering from Montana Tech and a PhD in civil engineering from Washington State University. For his dissertation, Steve studied the impacts on mercury fate and transport through the aquatic food in relation to lake and reservoir treatment technologies. Steve has over 5 years of experience within the last 15 years investigating mercury contaminated mine sites, including system biogeochemical fate and transport, and identification of cleanup alternatives and mitigation techniques. He has 15 years of experience using data collection and analysis of low-level mercury. So I will turn it over to Steve.
Okay, thank you. I'm trying to make sure I share the right screen here. Let's see. Right. Is that coming through?
Yep, there you go.
Are you seeing the, let's see, are you seeing the presentation slide or are you seeing the note slide?
We're seeing the presenters.
Yeah, we got
Okay.
You got to swap screens, Steve.
Oh, we got to swap screens. Okay, so how about that?
Perfect.
Great.
That works? Okay.
Yes.
All right, well, thanks for having me here. I'm happy to come and talk about one of my favorite topics. So today, what I want to discuss is mercury-related impacts to mine sites, and a lot of this is going to relate to West Coast issues where there's a lot of old mercury and gold mining sites, and typically with every mercury and gold mining site downstream somewhere, it ends up being some sort of mercury contamination issue and ultimately a food web uptake of mercury and then associated food web advisories. And so what I want to talk about today is kind of laser focus in on one of the identified technologies that everyone's really excited about, but is not well implemented. There's not a lot of case studies out there demonstrating it. And so this is kind of like a call to arms. We need to get more folks out there trying treatability studies or applying oxygenation to these receiving water bodies that are contaminated with mercury if we're going to really address some of these issues with food web uptake. So to start off, just kind of a brief overview of what we'll go through. I'm sure there's some folks on the phone that don't really have that big of a mercury background associated with mining. Mercury is kind of a tricky animal when it comes to how it operates in the aquatic environment as compared to other metals. Its concentrations at very low level are a lot more relevant than other metals that are very low level. And its behavior in the aquatic environment is oftentimes counterintuitive as compared to other metals. So we're going to talk about, the growing concern with mercury. It's the Food Web advisories, its dynamics in aquatic ecosystems, some analytical tools we use to figure out what's going on, especially when we get those really, 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 really small concentrations that still have an impact. And then look at some of the oxygen management strategies and some of the things I'd like to see happen moving forward. So we'll start out here with growing concern of mercury. If you're not familiar with the history, the very first entry onto the world stage of mercury as a problem in the food web came from Minamata, Japan, where an acetaldehyde production facility dumped 27 tons of methyl mercury right into the bay. Now, mercury has to be in an organic form, methyl mercury, to build up in the food web. And typically, what's released from mining or other industrial sites is either elemental or inorganic mercury, and it has to, through some sort of natural process, become methylated and then subsequently go up into the food web. Well, here they were a byproduct of their production was methyl mercury, so they didn't even have to worry about it being transformed into the organic form, and they dumped it straight into the bay. And so, the first cases started popping up in the late 50s. 900 people died from eating fish, and over 2 million people with severe health effects. I mean, I just went to the Mercury conference as a global pollutant over in Poland last year, and there was a speaker there who had physical impacts from this event. He was in utero at the time, and his mother consumed contaminated fish. So this is where it kind of came on the stage. Over the years, the United States have been adding fish consumption advisories all over. It used to be a pretty common industrial consumable, and especially in the West Coast, it was heavily mined or used to mine gold. And so every state now has a consumption advisory. The tan states here represent states that have individual water body advisories. The blue states are states that a lot of them, they just couldn't find any pattern in how to recommend one versus the other, so they issued a blanket advisory over the whole state. In California, there's a lot of work to be done there. The BLM has identified over 25,000 abandoned mine sites, and with another identified 66,000 features throughout California. This map here shows different gold, mercury, and silver mines. So the yellow dots here all represent identified abandoned gold mines. The red dots are old abandoned mercury mine sites, so mining cinnabar. And then the black sites are silver, and they used to mine silver very similarly how they mined gold, and they use mercury in that process. So oftentimes those are fairly contaminated with mercury as well. In California, because they have such a mercury problem associated with all this historic mining, they are starting to do something new with TMDLs that aren't traditional. So if you're used to dealing with TMDLs, these kind of sound funny when they start saying, okay, we're gonna give you a fish tissue target. So here's a watershed. If you are managing like a reservoir downstream of a mine, you're gonna have to start meeting a fish tissue target by a certain date. And there's not a lot of success stories of big reservoirs doing this. There's a few, Lake Onondaga in New York. They've been throwing everything but the kitchen sink at that site, and they've had some success there. But there's a lot of other places where they've tried to work out source control, and they still have lingering problems with concentrations of mercury in fish tissue. And so it's a very real problem that California is dealing with, and they have plenty of sites to go around. So let's get into what's going on with mercury and how it works. So this is kind of a conceptual model of a water column with overlying a sediment bed here. And down here in this top upper part of the sediment, I have lists of different oxic species that are present depending on what's going on in the overlying water. And so if you have a nice oxic water column above your sediments, you have some oxygen penetration into the surface sediments. What you're going to have is a lot of oxic iron and manganese species, metal oxides that can sequester mercury associated with DOC. It binds nutrients, things stay fairly stable at the surface sediments, except for, washout of large streams and whatnot. But it's a fairly stable condition right here. You don't have a lot of anaerobic activity except for it's pushed other than what's deep in the sediment. And so this is a nice condition where you typically see the sediment as a sink. As you burn through your oxic species, say the oxygen in the water is depleted, you start marching down these oxic species. You run through your metals, you start reducing your manganese, then iron, and they start becoming reduced and soluble. They release their compounds that are sequestered, getting an enrichment of element or inorganic mercury, DOC, and nutrients. And once you've burned through a big pool of your oxidized metals, you then go into a situation where you have sulfate reduction at the surface sediments, and sulfate reducing bacteria facilitate that reduction, and they are the primary bad actors in that process of converting inorganic mercury to methyl mercury. And so oftentimes when you see presence of sulfide start enriching in the bottom waters, you will then start seeing an enrichment of methyl mercury. And that's the component that will eventually partition into algae and move up the food web. Now this happens fairly quickly. Now this is a reservoir that had an oxygen, hypoliminetic oxygenation system where they were pumping oxygen in and maintaining oxygenated levels for a drinking water plant, I believe, where they wanted to keep metals out of the water so they didn't have to remove iron and manganese in their drinking water process. Well, so this window here is about a day and a half where they shut the system down. They stopped adding oxygen, right? So these three figures with depth of the water column on the left and then time series on the bottom, and this color code of oxygen, red being the lack of oxygen going to 0. This is just a blow up. So here's the full water column. You don't see much of anything happening through that shut off, and nothing much looks different, right? But if you blow it up into the millimeter scale here, you start seeing that at the sediment surface itself, you have a depletion of oxygen that was fairly rapid. Didn't take more than almost half a day before that went anoxic. And then it maintained an anoxic condition till almost a week. So almost a week after that thing shut down and they turned it back on, did it start becoming oxygenated. And this whole time while this is sitting here on a very small scale, it's releasing reduced compounds. And so this is a very rapid process. And if you don't look at these processes at a very small scale, you might not see what exactly is happening. And so if you had a system where you maintained fairly reasonable oxygen concentrations, but you didn't look real close, you might still have anoxic sediments and they're going anaerobic and releasing compounds and not know it. And then if you have a system that's causing advection, those constituents can be transported and move around in the system more than they would have if they had been just left alone. So mercury has a pretty complex relationship with itself. Total mercury and methyl mercury don't track well. I mean, typically when we reduce total mercury, we see a subsequent reduction in methyl mercury, but it's not linear. So over here on the left, we have percent methyl mercury versus total and a whole bunch of contaminated mercury sites. And we see with lowering concentrations of total mercury, we have an increasing percentage of methyl mercury. And there's a lot of reasons for that, but it shows that it's not just the presence of total mercury that dictates what's happening and how much methyl mercury we should expect. There's a lot of other factors at play here. Sometimes at higher concentrations of total mercury, it induces a detoxification mechanism that gets rid of methyl mercury. There's all sorts of interactions with nutrient cycling and the presence of oxic species that control it. And so it's a very dynamic thing, and there's a lot of approaches that revolve around just reduce total mercury and everything will be fine. Just remove total mercury and everything will be fine. Well, that turns out to oftentimes not be the case, and you reduce your total mercury to a certain target and you still have problems with methyl mercury getting into the food web. Over here is an example of several sites that have had pretty significant reductions in source control, and yet they still have problems with methylmercury in the food web. So this is fish tissue concentration after pre and post remediation, the black bars being pre-remediation, the gray bars being post. They've, in a lot of these sites, they've had pretty significant reductions in methylmercury, but they still pose a problem. So if you're above here, this is the consumption guideline, 0.3 micrograms per kilogram. It's the US criteria, federal criteria. If you're above that, you need to have a fish consumption advisory, and you must limit your intake, or else you will start seeing some residual effects from mercury contamination. And there's if you want to kind of a scary Google search is search some celebrities that have had mercury contamination because they've chosen to buy high-end food web fish from grocery stores and ended up giving themselves mercury poisoning, and they lose their balance, they have a hard time walking. There's some scary stories out there of that. So this is what the scenario is, right? So the biomagnification of mercury is pretty significant, and this is why we need to look at such low concentrations, because the transition from water to algae alone is 100,000 time concentration factor. From methylmercury in water to algae, 100,000 times. And then each subsequent step up the food web, you have about a 2 to 5 time concentration increase. So by the time you get up to predator fish, you can be, sub part per trillion level in your water, and you can still be well over the 300 part per billion in your predator fish. So let's look at some analytical tools that are required to take a look at this. So trace mercury analysis needs to be able to get to sub part per trillion levels. And in the case of methylmercury, you need to get down to 0.1 or below nanograms per liter to really be able to see what's going on, because you can have concentrations of methylmercury below 0.1 nanograms per liter that equate to above consumption guidelines in fish tissue if the conditions of uptake are right. And so these are very sensitive techniques that are very well proven. There's an EPA method for them. But one of the kickers here, and some of the biggest mistakes I see when you're dealing with such tiny concentrations and you have a really, really, really sensitive analytical capability, is you need to have the specific methods for collecting the sample so that you don't contaminate it. Because it's really easy to contaminate a sample that's got mercury concentrations less than a nanogram per liter. I mean, you have many folks, especially adults, have black fillings in their teeth, and those often are mercury based. So you have a little bit of mercury vapor associated with your breath. So you got to make sure you protect the sample from yourself. There's so those are the sample collection gets to be just as important as the analytical technique. It's important to take a bunch of different types of parameters when you're trying to figure out what the behavior of mercury methylation and uptake is. So you want to grab DO, what's going on with the oxygen, how aerobic or anaerobic is the system. DOC is partitions with inorganic and methylmercury species, in particular the SUVA fraction, which is the aromatic fraction of DOC. It's a strong ligand for mercury. Nutrients, getting a idea of what's happening with your nutrient cycle will give you an idea of productivity of the system. Iron and manganese is a nice surrogate indicator of redox conditions in your system, and a little alarm bell that if these are starting to show up, then sulfide is going to start showing up here soon. And then sulfide and sulfate tell you a bit about what's going on with sulfate reducing bacteria. There's a bunch of new innovative technologies for evaluating mercury in sediments. This diffusion gradient thin film passive sampler, the DGTs, they are a passive sampler that come into equilibrium with the pore water, and you can cut them into increments and get total and methylmercury values at depth in your sediment, and it's just telling you what's lay-bound and ready to partition onto some substrate. There's speciation techniques that have been around. There's now an EPA approved method for fractionating groups of mercury species. It's more operationally defined, but it tells you, how relative fractions of what's mobile and what's not in your sediment. And then there's the mercury isotope fingerprinting, which is really neat because it can tell you it's a lot of information about sources. So each ore body has its own unique, or usually has a fairly unique isotope signature. And so if you have a receiving body water that's contaminated in several potential sites upstream, you can compare their isotope signature and get a better handle on where it's really coming from. So I'm going to talk a little bit about management strategies here associated with oxygen, and it's been studied to death in the lab. There's all sorts of incubation studies that have, proof of concept shown this to be, an effective potential tool. We've seen how the production of methylmercury is heavily associated with anaerobic microbial activity, but we just don't have that many real world examples of the technology being implemented. And the technologies that have been implemented might not be the most optimal for what we're trying to get at with mercury. So a little bit on proof of concept here. This is a chamber study performed by Mark Patel's group out of the University of California, Merced. And he took a suite of chambers from 2 different lakes that are heavily impacted by mercury, and this suite of incubations over here is showing methylmercury in Almaden Lake and Guadalupe Reservoir, and the white bars are aerobic and the black bars are anaerobic. And you can see in both incubations, both lakes, you have a reduction of flux in the sediment of methylmercury. In Almaden Lake, you have actually a negative flux, so it's pulling methylmercury out of the water or degrading it in some form. And in the anaerobic conditions, you are releasing methylmercury into the chamber water. In Guadalupe, you have a significant release of methylmercury into the chamber water, and a reduction, still a release, but a reduction in the aerobic phase. And there's a different source of mercury for these 2 reservoirs, and that translates out pretty in an interesting way that there's a lot of cinnabar and metacinnabar in the Guadalupe Reservoir. And because of that, there is a phenomenon that can release total mercury in oxidized sediments if you have a lot of that original source material in it. A lot of reservoirs that are further downstream, you don't get a lot of that raw product or that raw ore into the sediment bed. And so here you're actually oxidizing the mineral, and it's releasing during the oxic phase. Here you have more traditional response of mercury, the sediments acting as a sink during the oxic phase and then a source during the anaerobic phase. But the big proof of concept here is what happens with methylmercury. And this is what we see almost all the time is if you get those sediments nice and oxidized, you don't typically have a lot of methylmercury coming out of the sediments. And contrary, when you have a nice anaerobic sediment water interface, you start really producing methylmercury, especially if you have a lot of mercury present in the sediment. So there's several different types of oxygen delivery technologies that have been used for years. It's a technology used to fight hypolimnetic eutrophication. So that's just a fancy way of saying productivity in the bottom waters of lakes and reservoirs, where you have lots of internal nutrient loading. You get a lot of metals coming out of the sediments. And what it does is it consumes all the oxygen in the cold bottom water portion of the lake, and then your cold water fishery can't survive, and all sorts of nasty stuff comes out of the sediment. So they've been fighting that for years. Originally they used air, but air only has 20% oxygen, so the transfer rate's not very effective. So a lot of these applications have switched over to pure oxygen. They either build an oxygen generator on the bank, or they truck in a tanker of liquid oxygen and use that as a source. And what the technologies used in context with mercury, or evaluated in context of mercury, are these line diffusers, which are like a garden soaker hose that they pull out into the reservoir and sink. And then you get this nice pin bubbles that come up and form a line, an upward advective plume that looks something like this. It's a cross section where the plume goes up, diffuses, oxygen diffuses from the bubbles into the water, and then you have oxygenated water that flows out into the lake and comes around. And it's used a lot for opening up fish habitat. Unfortunately, in some applications, it doesn't really get down here into the sediment in all cases. And so sometimes you still have an anoxic sediment bottom. Here's an application where they used it in a reservoir. An example here, the reason you'd want to maybe do this with one of those bubble plumes is to open up fish habitat here in a reservoir, or if they're required to meet certain oxygen requirements. This is the level of the outlet for the reservoir. But you can also see that there's plenty of anoxic sediment surface down here, and you have an upward advective plume potentially drawing up reduced compounds up higher up into the food web. Here is an example of the project I worked on for my PhD. That's Twin Lakes. This is North Twin up here. This is South Twin down here. They treated North Twin. In the untreated lake, we had a lot of enrichment of manganese and mercury in the bottom water above the sediment, but the thermocline was way up in here, so there wasn't a lot of transfer between the food web and accumulated methylmercury because it was all anoxic, so the zooplankton and fish weren't really diving down. Here where we treated it, it wasn't installed for mercury, but it was installed to open up fish habitat. But we saw a negative effect here of drawing up methylmercury up higher up into the water column, lower concentrations, but now there's a little bit more food web overlap. So this would be an application where they would need to tweak the system if they were wanting to address mercury in it, because you have this now upward advective process that, you know, pulls up compounds coming out of reduced sediments. What I think the application should move towards are examples like the submerged contact chamber, which it's a Spiess cone, pumps water down through the cone. The water decreases in velocity as the cone cross-sectional area increases. You're piping in oxygen gas, which saturates the water, and you just get pure water coming out. You don't have a bubble plume. You just have saturated water diffusing across the sediment water interface. There is a case in Comanche Reservoir that installed one of these in the early 90s, court ordered because of their requirements for having the reservoir and their bottom cold water was going anoxic, so they were court ordered to install one of these. It's a pretty large reservoir, over 400,000 acre feet. You know, it's 56 feet deep. They've been successful in maintaining an oxic bottom, and they've been running it for years. This little triangle with dashes here is just after installation, and these ball and line markings here show 11 years later. What's not shown here is that they've dropped the oxygen delivery to the system about 2/3 over the course of that 11 years because the sediment oxygen demand was going down. In a big system like this, so this is a pretty large reservoir, was about 3.1 million. Their annual operating costs over 20 years averaged about $285,000. Hodges Reservoir, it's an exciting opportunity where they just installed this, I think, about 2 months ago. And they are installing it partly to address their mercury problem. And so it'll be really interesting to track the results as they install this new type of application targeting mercury accumulation in the water column, because it doesn't have an upward plume and just delivers saturated water at the sediment water interface. And this system, which had a pretty big deficit of dissolved oxygen. You can see here's an isopleth of time versus elevation into the water column. And basically the entire hypolimnion was anoxic, and you had this enrichment of methylmercury up into the water column. The cost for this system it's not quite as big of a reservoir, but 30,000 acre feet. It's about 100 feet deep, so a little bit deeper. Their operational cost was $220,000 a year, and the cost for this system new was $4 million. And then I wanted to throw in just last minute here this smaller reservoir that we worked on in California. Very productive sediments. It's only about 1.5 miles long, a couple hundred feet wide, small ranch reservoir, extremely productive. It has a really high oxygen demand. Here's SOD on the Y scale here, different reservoirs and lakes around California. And this is the results from the chamber study we did to evaluate sediment oxygen demand. It's got an incredible oxygen demand, especially when it's mixed. So what we designed, we haven't implemented this, but we have the design and cost for it as this side stream oxygenator, which pulls water out of the water column with an oxygen source, and then with pressure saturates the water and then delivers it back down into the smaller reservoir. This smaller reservoir has a cost much less than those larger reservoirs of $120,000 or $150,000 to $200,000. So that's a quick snapshot of the scenario with oxygen treatments for mercury and mining impacted reservoirs. It's a tricky topic. It's very counterintuitive how it behaves compared to other metals. You have to really be careful on how you define everything that's influencing it. There's a lot of negative feedbacks that are hard to predict. So there's definitely a need for more applications of oxygen delivery systems and a variety of oxygen delivery systems. So we just put more tools in the toolkit. We have a lot of theoretical tools. We don't really have a lot of applications to draw on, and we need that. Okay, with that, I'll take any questions.
Okay, great. Thank you, Steve. You do have a couple of questions. The first one from Millie Olson. Let's see. Have there been any studies on long-term chemical speciation differences or macrobial community differences caused by removing the anoxic zone in the water bodies?
As far as a shift in the communities, if you don't allow that to set in?
Yeah, I don't know.
Well, okay, so, you have a completely different suite of organisms that are going to take over in anaerobic sediments. I think the take home there, I'm not sure exactly if this is going to get at our question, but the reservoirs and lakes, lakes in particular, don't typically, natural settings don't usually end up with this very heavily eutrophic bottom water. There are some examples where that is natural, but most of these sites are from some sort of human impact. And so they have excessive nutrient runoff into their system, and they are at an unnatural state operating like this as is. And so by maintaining oxygenated conditions, lowering this SOD, while at the same time working on source control, not only of your contaminants, but things like nutrients. You try to work this water body back into a healthy state. Reservoirs are tough because they never were saturated. This is dry land that was flooded, and if they didn't go and take the topsoil off before they flooded, there's a lot of stuff under there to cause productivity to get out of control.
Okay, the next question. Okay, I don't know what the, okay. Mercury tends to absorb to MnO2, which forms with the help of algae via photosynthesis. It looked like there was a correlation of mercury sequestration with decreasing Mn concentrations in the water column. If you add oxygen, you should precipitate more MnO2, right?
Right.
Okay. Any other questions? Okay, so thank you very much, Steve. That was an excellent presentation. We are going to be breaking for lunch now. We are going to stay on Zoom for the afternoon, just since everyone is already on. It's established, people know where to go. So we are just going to maintain Zoom for the afternoon session. So just come back to this same link at 1:30. We're also going to draw for a couple of Amazon gift cards right after lunch. So come on back at 1:30 and we'll get going again. Thank you. Yeah.
Everywhere we're operating, we're the largest private employer there. People are engaged with the mines and they take ownership of the mines. And as a result, the company is committed to the community.
Before we begin, we think of the end. During the operation, how do we minimize our impact and protect the environment? And then ultimately, how do we restore and reclaim that land to other productive uses?
We have a responsibility to our workers that they can stay safe. We have a responsibility to the communities that the workers will return home for dinner at night. We have a responsibility to our shareholders. We have a responsibility to governments that we will make a profit and we will pay taxes in order to support the general infrastructure. We invest in the communities.
It's that we operate in the best jurisdictions in the world, in Mexico, Canada, and the United States. And today that's more important in a precious metals company than almost anything else in the world.
The company that has the right culture, they're going to do it responsibly all over the world. And in the United States, though, you have the best environment to do it the best, right? You've got great laws, you've got great workforce, you have great minerals.
We have a plan, we have the team, we have the skill set, we've got the operators. And when you operate well in a community, it shows in the happiness of the workers and the happiness of the community.
Instead of saying, that's not my job, you say, what can I do to help? So I'd rather it be done here where we can do it responsibly and you have a company like Hecla that does it, that cares, because we need these resources.
I'm Phil Baker, CEO of Hecla Mining, and we're responsible,
safe,
Responsible, safe, and innovative.
Mal Foster and Alongi is an integrated multidisciplinary firm consulting in environmental services, engineering, planning and development, GIS and data analysis, communications, and health and safety. We are passionate about working with clients to provide solutions for complicated sites throughout the Pacific Northwest. MFA has worked with the Coeur d'Alene Trust on remediation of the Bunker Hill Mining and Metallurgical Superfund site since 2010. MFA assists in program management and strategy, tracks documents and data, conducts site characterization and monitoring, and evaluates remedial action designs.
In there, that's your account. That's got your picture in there. You're logged in, but it's under. I think there's a lot of overlap between the two because every time you were saying like styles, yeah. But it's nice that we got pictures in there. You know, like most people and CT work, learning people can move. Yeah, of course, Bruno does. So this is what you're being presented with. I would mute yourself.
Welcome to SVL Analytical. We've worked with thousands of clients from around the U.S. and the world. We prioritize data integrity, quality lab practices, and personalized service with every analysis. At SVL, our team of professionals genuinely care about the relationships with our clients and take pride in the work we do, making SVL Analytical a trusted partner in environmental laboratory testing for nearly 50 years. Our clients' analytical testing results are used around the world to make critical, timely decisions. When you need streamlined and accurate results with a customer-centric approach, SVL is ready.
Hi, I'm Tim Van Weingarten, Vice President of Business Development at ACZ Laboratories. I've worked at ACZ for the last 30 years. ACZ has been a proud sponsor of Montana Tech's Mine Design, Operations, and Closure Conference for the past 25 years. ACZ was founded in 1980 as a support service to the mining industry. We support all aspects of the mine life cycle, from baseline water quality monitoring through operations permitting to closure, with our in-house static and kinetic testing capabilities that include AVA and humidity cell testing. ACZ provides litigation quality data with inorganic, organic, and radiochemical testing capabilities all in one location, something that large chain labs can't provide. Experience matters. ACZ's PM and client service staff have over 110 years of combined experience with ACZ. Please contact us at sales@acz.com or 1-800-334-5493 for a quote on your next project. Enjoy the conference.
From climate change and rising sea levels to rapid urbanization and pressure on natural resources, our world is a more complex place. Arcadis helps you navigate this complexity by understanding the bigger picture. Whether it is maximizing space in cities, making wasteland habitable, or simply taking what you do further, we deliver exceptional and sustainable outcomes safely and consistently. Connecting your vision to our know-how. Our people work collaboratively to create value through built and natural assets that work in harmony with their surroundings. From shopping centers in Shanghai or clean water in Sao Paulo, to new rail systems in Doha and reducing air pollution in Los Angeles. Our global operations and diverse experience mean we apply collective wisdom to every challenge, big and small. In this way, our experience protecting the Dutch coast for generations is applied to securing New York's flood defenses today. So, whatever your challenge, our teams bring the necessary perspective to provide the right answers now and in the future. Arcadis, improving quality of life.
At CDM Smith, we are committed to making a difference for our clients, our people, our communities, and our world. Since 1947, we have been solving the most complex environmental and infrastructure challenges. Whether it's making every precious drop of water count through safe supplies, reliable conveyance and sustainable reuse, designing remediation systems and restoring ecosystems, or leveraging emerging technologies and multimodal strategies to connect people, places, and goods. We've been giving back. We are global citizens committed to helping communities. our own, and those in need around the world. And perhaps most importantly, we've been making the world a bit better along the way. We're CDM Smith, and we can't wait to work with you.
Energy Laboratories, established in 1952, has been committed to analytical excellence ever since. We're committed to providing exceptional customer service experience with dedicated project managers available for assistance at any time, from the first contact with us through the final report being in your hand, and any questions you may have after that. We're a full-service analytical laboratory specializing in water, soils, and organic analysis, and now offering such specialties as radiochemistry analysis, aquatic toxicity, and PFAS/PFOA. We work with a broad range of partners in industries such as municipalities, drinking water and waste treatment, through mine exploration and reclamation, monitoring wells, stormwater, waste characterization, petroleum production and exploration, and with agencies from federal agencies to industry and manufacturing, all the way to individuals interested in their private well or garden soils, and working with clients all the way from Alaska to Mississippi. We provide sampling supplies and sample containers, preservatives, paperwork available for local pickup or shipped directly to your location. We provide convenient prepaid return shipping labels to get your samples back to us as effortlessly as possible. With 4 locations to serve you across Montana and Wyoming, give us a call today to set up your next project. More information can be found at energylab.com.
I'm Eric Mears. I'm with Haley & Aldrich. I'm the market segment leader for our mining practice. I've been in the mining industry or working with the mining industry now for about 25 years. We work for construction materials clients, we work for industrial minerals clients, and we also work for hard rock clients, which are the base and precious metals. Well, the material at this site ends up in a lot of different places: roads and highways and infrastructure and houses and sidewalks and schools. Materials that are mined here are really the building blocks of our society. And without sand and gravel mining, you don't have the modern society that we have today. We look for solutions that fix kind of the bigger picture. We're not just out there putting a hammer on a nail head. We're out there saying, okay, who are the stakeholders? What are the issues involved? What are the kind of interchangeable pieces here? Things that make a difference when you're trying to build a solution that meets multiple needs. We have our core practitioners, the people that have had their boots on the ground on mining sites, have often worked in the mining industry. We've got one profit and loss center, which doesn't silo our resources and our people. We don't compete against each other to solve our clients' problems. We can take diverse experience in different industries and apply them to deliver some innovative solutions for our mining clients. We ask a lot of questions. We ask questions about, okay, what are the things that are immediately right in front of us? What do we need to fix right now? Who are the stakeholders involved? What are the other pieces of the puzzle? The idea is that we come to the table once we've done a lot of listening with solutions that really fit our clients' needs.
Everywhere we're operating, we're the largest private employer there. People are engaged with the mines and they take ownership of the mines. And as a result, the company is committed to the community.
Before we begin, we think of the end. During the operation, how do we minimize our impact and protect the environment? And then ultimately, how do we restore and reclaim that land to other productive uses?
We have a responsibility to our workers that they can stay safe. We have a responsibility to the communities that the workers will return home for dinner at night. We have a responsibility to our shareholders. We have a responsibility to governments that we will make a profit and we will pay taxes in order to support the general infrastructure. We invest in the communities.
It's that we operate in the best jurisdictions in the world, in Mexico, Canada.
Time with Resource West. But before we get to Robert, I just kind of want to briefly once again thank our sponsors. You've been seeing a few times, during breaks and whatnot. We've been running videos from our sponsors. They are listed on the conference website as well. But our mother lode sponsors, the BLM, Montana DEQ, U.S. Forest Service, and Montana Tech, those are our three, Montana Tech, yes, but the 3 main sponsors are the 3 agencies, and they are the backbone of this conference, and without their support, we would not be here. So a huge shout out and thank you to those 3 agencies. Also, our platinum sponsor is Sibanye-Stillwater. Gold sponsors, CDM Smith, Hecla Mining Company, and Pioneer Technical Services. We've got several silver sponsors, ERO Resources Corporation, Haley and Aldrich, Hydrometrics, Mal Foster and Alonji, Morrison Merrily, Rio Tinto, Sandfire Resources America, and Spectrum Engineering and Environmental. And lastly, our copper sponsors are ACZ Laboratories, probably one of our oldest sponsors, if not the oldest, outside of the agencies. Arcadis, Energy Laboratories, Montgomery and Associates, SVL Analytics, and Water and Environmental Technologies. So a huge thank you to all of the sponsors. We appreciate your support, especially this year with everything being so crazy and different and out of sorts. I immensely appreciate all the sponsors staying with us and supporting us so that we could get this event off the ground. Okay, so, and then, like I mentioned before we went to lunch, we're gonna stay with Zoom. Everyone's pretty much established here. Everyone's ready to roll with it, so we're gonna stay on Zoom. These presentations will be recorded and they will later appear. We will have a YouTube site where these presentations will appear, so you can go back and watch them in their entirety, and I will send out a notice once the videos are up and accessible. So before we get started with Robert, I am going to draw for 3 $25 Amazon gift cards. I will just send an e-card to the winners. So can't look in there. The first winner is Kevin Kelly. Kevin here? Okay. And next winner is Garrett Mannion. And our third winner for today is Jake Mormon. So those 3 individuals, sometime this week, will be getting an email from me with an e-card from Amazon for $25. Thank you all once again, and we will get this rolling with Robert Ballantyne, who I should probably announce. Okay, so Robert served in the United States as a U.S. Marine. He is an electrical engineer with his follow-on education concentrating on molecular and atomic I don't know, whatever. His body of science research work focuses on environmental monitoring, mitigation, and remediation systems design, with an emphasis on waste stream reduction. His current role as Director of Research and Development for RWI Evaporation has allowed him to pursue the raw scientific research into ways to fundamentally change environmental mitigation markets and methods. So with that, I will welcome Robert, and thank you.
Thank you very much. Appreciate the opportunity. Was here in 2012 to present to the Mine Closure Conference, and ended up back in 2018. This is a rather short cycle for me, but we have some very interesting information moving on. Let me kill this camera here, see if this will work a little better. I don't think there's enough bandwidth.
Robert, you need to turn off screen share and then turn it back on.
Awesome. All right, it is working now.
All right, we got it up.
Yep, it's working.
Yes, you're fine.
Okay, let's rock on then. So was here in 2012 originally, started when I first started the research, then was back in 2018 to present a little bit more of the research. Today I'm going to present a lot of the science on the droplet aerosol control and the problems that we have been curing with that. Mostly I'm going to tell you about what we found so that you can use it yourself. Of course, we do turn this science into machines. This is what prompted us to get into taking a look at what was going on with impacted waters when they were evaporated. We were like many other companies back in the beginning. We were using converted snow machines. They all had the same problem. They assumed that they were using clean water. Nobody made snow with impacted waters. It wasn't conducive to return visits. So Rule 40 FCFR 51300 started coming through the promulgation process. We realized for the first time, the rule was actually wrote because of the Grand Canyon and people not being able to see all the way across the Grand Canyon. The federal government was upset. They wanted some type of controls on air pollutants in the form of particulate matter. So the visual impairment rule came along, or what was eventually known as the regional haze rule, which we realized was going to allow state agencies, in fact, it was going to put some pressure on state agencies to really start looking at particulate matter. And it was going to give them tools to enforce it. So we stopped with our snow blowing machines and went back to the drawing board. That's where all of this research that I present comes from. It comes from trying to clean this up. So studying the dry aerosol compounds and how they were formed in the enhanced evaporation process required us first to look at our old equipment, which was pretty much the same thing everybody else did. They copied a Snowmaker, put a slightly different nozzle on it, created large surface area to get rid of water. Unfortunately, there was a lot of problems with that. The first big problem that we identified, which turned out to be the only problem, but it happened in multiple forms, was droplet destabilization. By controlling turbulence and droplet size, destabilization can be mitigated. The droplets that are introduced into a converted Snowmaker destabilize almost instantly. They fracture into smaller droplets. They dry out in flight. This makes the ion content of the water turn into a dry aerosol compound, and it's usually below 10 microns. We'll get into sedimentation rates, but once you get below about 100 microns, you have no idea where this is going to land. So your pollution plume is going to be hundreds of miles. This large particulate load in the atmosphere, you know, it puts people in violation of air quality standards. A lot of times very hard to see. And so this is not going to show up until vegetation is dying some 8 to 10 years later. where a significant amount of shareholder value is going to be in jeopardy because of the cleanup cost. Picture originally shown in 2018, but I needed a way to visualize for people what these snowmakers were doing. This is our original 75 horsepower machine. We called it the Great White. And what I'm doing, I have the sun behind me, and I'm using an infrared flare camera to visualize that dry aerosol plume as it lofts up into the atmosphere. The green color here is wet bulb. That is the temperature water will reach. As long as you see some green, there's still water in that droplet. As soon as it goes to the light blue, there's no longer any hydroxyl molecule left in the plume in that part of the dry aerosol plume. So this is now a free-floating dry aerosol compound. I am using a 50,000 TDS solution that I made in our 20,000 gallon evaporative test area. We have a 5-acre site where I control everything that comes on and goes off of it except for what blows in from the West Coast, which we actually ended up having to monitor because it was making our hypothesis not line up with the empirical data. But what we're visualizing here is we're using the sun's reflective energy just to show what is going on with the dry aerosol. In this case, sodium chloride, common table salt, potassium chloride, common table salt for cardiac patients. This was the problem. As the animation runs, the droplet begins to concentrate, which is nice. We like the droplet to fly. We like droplets getting smaller because droplets give us our surface area. But then the problem at the end is the droplet disappears. Now, once nothing wants to exist as an ion anymore, it must compound out. So we have the sodium chloride forming and the potassium chloride forming. We did a pretty in-depth study of exactly how are these droplets forming. What we found was that the droplets are destabilizing at speed. So there was a rush, there still is a rush for people pushing the older technologies to push faster and faster, more and more horsepower. You see one, out of the Queen's Penal Colony, Australia, where they're now pushing 200 horsepower and some 170 miles an hour. This causes the droplet to destabilize, stretch into funny shapes, where it finally fractures. The surface tension allows it to fracture. It fractures into micro daughter particles. Of course, a daughter particle is going to have to be smaller than the original volume of the main droplet. And the more times it shatters, the smaller the droplet gets. The turbulence entrains the droplets, so they have almost no sedimentation rate. They're being generated in a 20 micron to 5 micron level. We were pushing these droplets at roughly 100 miles an hour to 110 miles an hour to watch what was happening to them. We were able to replicate all of this. There are 6 modes of failure for droplets at speed. Droplet can just split, and depending on the acceleration rate of the turbulent air it's being pushed into, the droplet can split again and again and again until it no longer has enough mass, or it reaches the speed of the flow when it stops deforming. The droplet can burst like a balloon, where it bags up, it flattens out, it starts to form a bubble. Depending on what's impacting the water, and its surface tension will depend on how much bubble area forms before it shatters. The longer the elongation, the smaller the micro daughter particles that are going to be created. You have a funny failure mode where at speed you get a disk, then you get a pestle in the center and an outer disk, and then the whole thing falls apart about T plus 15 milliseconds. You get a sheeting, it disks out, and it just kind of bleeds off like a comet tail off of the edges, leaving a trail of 5 to 10 micron droplets behind it. Then you get a shattering, and last you can get a catastrophic breakup where all 5 of the others happen at the same time. The problem with this becomes if you don't pay attention to the droplet breakup when you're trying to evaporate wastewater by making increased surface areas, you will lose control of the trajectory of the droplet. Sedimentation rates get up into the 66 and 80 minute range for a 10-foot drop, that's in a dead still wind tunnel. It's just never going to happen out in the open atmosphere where you've got hysteresis happening, turbulence of all types and in different directions happening, physical and civil features in the way. This is a high-speed camera image of a droplet being pushed in front of a 75-mile-an-hour flow. The droplet at T0 milliseconds is a 150 micron droplet. At T plus 4.7 milliseconds, we see that the droplet has already destabilized. It's begun to disk out and fold over on itself. At T plus 7 milliseconds, primary area of the droplet has shattered. There has been a secondary formation of several larger droplets. At T plus 10.3 milliseconds, those droplets have destabilized, creating a lot of microparticles in 2 still relatively large 50 micron to 20 micron droplets. At T plus 15 milliseconds in a 75-mile-an-hour wind, this droplet no longer exists, and it is not going to land anytime soon. There's about somewhere between 58 and 78 microdroplets there. They're all below 10 microns. There's a few that will make it to 15, but flying through the air as their surface area allows them to evaporate, they too will go below the 10 micron level. This is how we propose to solve the problem. We started taking a look at wet bulb temperatures and ambient temperatures, and at what rates do different size droplets evaporate? How is their surface area affected by flying them? To us, the simple solution was to keep the droplet whole, to start it off large enough that it was not going to dry out in flight, and to keep it stable enough that there was no way this droplet was going to form any type of micro daughter particle that would dry out during the course of its trajectory. We ran into a problem in that we came up with this, we got the droplet sizes right, and we'd mix up 50,000 TDS water, 20,000 gallons of it, and we would predict that, of course, after we evaporated 10,000 gallons, we would see 100,000 TDS of the leftover 10,000 gallons. And we never hit that. It was driving me nuts. We would go out, are the pumps eating it? What's happening to it? Is there some other kind of problem? We finally realized, okay, well, we understand now what the air is doing and how to turn it down to keep it from destabilizing droplets, but we never really looked closely at what was going on in the liquid delivery system. This was also compounded by the BLM in Colorado watching the use of some impact sprinklers, big irrigation guns trying to evaporate impacted waters and seeing vegetation die. We got to looking at what was happening when you push water at high pressure. This is a CFD, a flow simulation of our water nozzles. We usually use 30 in the ring. So I had to take them out because we didn't have, 2 computers weren't big enough to crunch the numbers. So this is 15 nozzles, which it could crunch the numbers on without blowing up. And the red area is the area where there is enough energy in the droplets being forced at accelerated rate just by the liquid pressure to shatter the droplet as well. So what we've discovered was we always thought the droplets would either combine or just bounce off of each other in the ring. When we got to looking at it real closely, what we found out is it's not the case at all. These droplets only bounce off of each other about 18% of the time. The rest of the time, they're hitting at angles that cause them to shatter into different formations. But all of them, because they start off with 150 micron size, any change to them, any loss of liquid, it means the droplets are small. So what we found was the droplets would break up into 6 basic failure modes. The droplet would bounce off of itself 1 out of 6 times. It would shatter into a large droplet and 2 smaller droplets times 2. It would shatter into a very large droplet and a smaller droplet times 4. It would shatter into 6 equally smaller droplets, or both droplets would shatter into 4 small droplets. This was a problem where these would then entrain in the airflow, even at low speed, fly up on the trajectory path and dry out in flight, releasing the dry aerosol problem we were seeing. This also finally explained why we could not predict the TDS at the end of the 10,000 gallon concentration. So what we ended up doing was developing a new way to add water droplets into an airflow. We cleaned up the airflow. We made the airflow not turbulent by doing a new type of knocker blade that allows this unit to create a well-formed flow that completes a helix in 150 feet instead of every 8 feet like our old snowmaker units did. In this simulation here with the center injection system, the red areas can still cause a shattering. There's still enough energy for that to happen. But right now we are down to losing less than 1% of our droplets to daughter particles. And we're moving rapidly now down to the 0.2% range. We greatly altered the breakup regime, and this finally gave us complete control of the plume, particularly the ion content of the plume as we were evaporating water through enhancement of the surface area. So we finally ended up with the ability to generate evaporation without a converted snowmaker. This is a high-speed image of the unit pushing 54 miles an hour, which is usually where we stay, and launching the droplets. This is a test unit. I'm running some nozzles inside so that the air gets pre-wetted. This is a video of the beta build of a trajectory system. This is 7 units. We replaced 5 40 horsepower units at 200 horsepower. This is gold cyanide heap leach tailings pile, and it's no longer in operation. It was 65 acres when we started. We brought her down below 30 acres now and continue on. The 7 units that replaced the original 200 horsepower draw a combined total of 35 horsepower. The predicted model from the science was for these to push about 22 gallons a minute evaporation up in the area of the mountains of Washington. And after we took a look at it with the telemetry, where we sonar the bottom of the tailings pond and we fly a drone over the shore area, we found that they are coming in at 20.89 gallons per minute evaporation with complete plume control. So we were able to predict where the TDS should end up and watch it concentrate in the deep end of the tailings pond. There's another view of it, just to kind of show you how the weighted droplet refuses to loft. And this again is that 7 spur jetty built out into the tailings pond. On the return to the beta testing of 7 units that we proposed would have these properties, they wanted to remove even more water. So we added another 8 units and ended up with 45 horsepower total. And we removed about 7.1 million gallons per month with those 15 units operating in an area of the country where it's about 84 degrees and usually roughly 68 to 72% humidity. It was a very interesting test and beta operation for us and for the client to get as much of the weight as possible off of the tailings impoundment. Now we were asked to create something that even had a smaller profile for plume. That became the downdraft evaporator system. So if you have fans and you're looking to get rid of water, you can really disturb the boundary layer with those fans, and it will do incredible things for your water loss. This test was done in a Nevada mine. This is an abandoned mine. They had an acid drainage problem that the state was very interested in them solving. We ended up starting out with 4 units. They're basically delivering an acre-foot of evaporation per week in that area of the country. We're at about 9,500 feet, so it doesn't get super warm down there. But we don't have any loss of plume. We're not painting the walls white. This picture was taken after 3 months of operation. We went down and installed another 8. It's about $100,000 in OpEx to run these systems because they're only drawing about 3.5 horsepower each. So to run these systems on solar would be about $100,000. If you have wind where we can put up a couple turbines, that also helps. Important point here is when you control the droplet size correctly through pressure modifications based on the evaporation rate, which is set by the difference between ambient air and wet bulb temperature, it is possible to keep everything contained in the pond where your shareholder value is protected from lawsuits for doing damage to the environment while you're still solving the problem. We're still pretty early into development of solutions. We get a lot of people asking us for things, but we are not finished yet perfecting the science and perfecting how our units can perform. I wanted to make sure you know the presentation will be put up like they always are on the Montana Tech site. And I want to acknowledge that we didn't invent any of this. This is our site, it works. There was a lot of people doing work on this before us. We're merely just trying to push the state of the art to get better pollution control and get the state of the art data out there so that other people trying to do their own evaporation projects can understand how to control the pollution. For us right now, big focus is on droplet control and droplet evaporation rate control by changing sizes and changing trajectory in real time using VFDs to change the motors. So we change the pressure on the nozzles to change the droplet size, and then we end up changing the RPM of the fan motors so that we can control how far this droplet is going to fly. That doesn't mean that's how you have to try and do it, but we want that information out there so that you people on the front lines who are dealing with these impacted waters and legacy mine water management and active mine water management at least have the information that we've discovered over the last 2 years since the last spoke, and what it has meant for us and the state of the art in the form of pollution control. So with that, I'm done, and I know everybody ate lunch, but if there's anybody still awake and not into lunch slumber, I can take questions.
Any questions for Robert? All righty, well, thank you very much, Robert. I appreciate it.
Thank you.
Nice presentation, good job. And we will then be moving on to our next presentation, which is by Cody Klein from CDM Smith.
Yep, hello.
Hi, Cody, how are you?
I'm doing well. How are you?
I'm good. Okay, so everyone, I'm going to introduce Cody. He is a civil engineer with a Bachelor's of Science in Civil Engineering from the University of Idaho. He holds a license as a professional engineer in the state of Idaho. His experience includes performing design and field engineering work for several remedial actions taking place as part of the Bunker Hill Mining and Metallurgical Superfund site in northern Idaho, as well as emergency field work for industrial clients. His work includes civil and remedial design and construction and assistance in compliance with federal, state, and local regulations. So welcome, Cody, and I will turn it over to you.
All right, well, thank you for the introduction. As she said, I'm Cody Klein with CDM Smith, and I know that our attention is a pretty hot commodity these days, so thank you for your attention over the next 25 minutes or so as I talk about the adaptive management and remedial design of the Canyon Complex repository. So today I'll be talking about a brief history of the Bunker Hill Superfund site and the Coeur d'Alene Trust. I'll discuss our problem statement with our project, some of the history of the SVNRT repository, the adaptive management process that we used in the design, some of our design considerations, and some of the design features. So back, the Silver Valley is located about 70 miles east of Spokane, Washington, along the I-90 corridor. And back in '83, the area was designated a Superfund site by the EPA because of the contamination from the historic mining and smelting operations that have been ongoing since the late 1800s. And in 2012, a ROD amendment discussed the selected remedies in the upper basin, which is where our site is located. Let me turn on my laser pointer. There we go. And the Coeur d'Alene Trust, back in 2009.
Cody, excuse me.
Yes?
I'm sorry to interrupt. Do you have a PowerPoint?
Is it not sharing?
No.
Oh, I thought this was, yes, I do. Sorry, I've been going through. Can you see either? Yeah, can you see either screen? I don't know what I'm.
No.
Okay, let's try this. Maybe the host has asked you to start your video. Is that how I share? Start a video? Sorry about this.
And then at the
Yeah, now if you share your screen.
Hit the green button.
Is it
There
sharing
you
now?
go.
Oh,
Yes, thank you.
yeah, sorry about that.
No, sorry to interrupt you. Go right
No,
ahead.
it would have been a bad presentation without the visual aid. So I'll just give you a quick shot for the recording of the other slides here. Okay, so back in 2009, the EPA announced their largest Superfund settlement to date in the sum of about $1.7 billion for cleanups across the country. About $500 million of that went towards the cleanup for the Bunker Hill Superfund site and went into the Coeur d'Alene Trust. And the trust works in conjunction with the EPA Region 10 on these projects. So the Canyon Complex Repository is located north of Wallace in the Canyon Creek watershed, about a mile and a half upstream from Wallace. So inside of the Canyon Creek watershed, we have estimates of upwards of 2 million cubic yards of material, of contaminated material. And the existing repository inside the watershed has a remaining capacity of around 750,000 cubic yards. And that remaining capacity isn't only allocated to wastes inside of Canyon Creek. It accepts waste from other sites inside the basin. There are limited locations for additional repositories inside Canyon Creek near the mine wastes that satisfy some of the siting criteria, which includes flat ground and avoids housing areas and historic tailings facilities. The existing SVNRT repository is currently loading zinc. The SVNRT repository is a failed repository near our construction site that we are going to address with our project. And early on, the SVNRT area was identified as a potential repository location for additional wastes, but was excluded due to some land ownership, I guess, concerns or issues. And we can use adaptive management to help find a viable solution to some of the issues that are presented with the site. So the SVNRT repository was constructed in 95. Was constructed in 95 to 99 as a multi-party endeavor funded by the Silver Valley Natural Resource Trust Fund. The repository was planned and developed as a voluntary, non-time critical CERCLA action, which was meant to remove materials contaminated with heavy metals from the floodplains and the adjacent properties in the area, and that waste was placed inside of the SVNRT repository in this location. They removed about 600,000 cubic yards of waste, and in our 2015 and 2017 site investigation as part of the Canyon Complex Repository design, we found that the materials had lead and zinc in concentrations of up to 53,000 parts per million and 30,500 parts per million, respectively. And as a quick side note, there's a little red dot on the map here. I actually grew up right there. So living and growing up near these sites and now being able to work on some solutions and help clean up my home area has been a pretty unique experience. My family's asking me questions about what we have going on all the time. So it's actually been pretty nice to have answers for them. So the SVNRT repository has some current issues in that it has water in contact with the waste pile, and that water is seeping out at the toe and is a very visible eyesore. And the SVNRT repository was one of the first sites that we as CDM were introduced to in the Valley. And we were told that we cannot let this type of situation happen in our future work. So we've been very mindful of this as we've progressed with our work in the Valley. There was a draft closure report written about the construction of this project, but it doesn't have much in the way of what was actually done. There's no specific info on what was done with foundation prep. There are some details of what was planned, but as we all know, sometimes plans change. Field fit kind of takes over in some instances. And some studies show that we have about 50 pounds of zinc loading into the Canyon Creek area from this particular site. And the top photo is from some site investigation that we had done back in 2015, and the lower photo, we have since started construction on this project. This was the bottom photo is a photo from 2019 during construction activities. So we have shown, we have some investigation info from some monitoring wells throughout the site that shows we have inadequate hydraulic isolation and kind of where that's occurring. We have perched water in the waste, and some wells indicate that the groundwater is actually coming up into the waste about 15 feet. And that's one of the big issues causing some of the loading from this site. The selected remedy for the SVNRT looked at several options, capping it in place, which would have low effectiveness because we have groundwater coming in from below, source control with a complete removal of the waste and placement elsewhere, which was not chosen because the estimated cost was far too high. And the selected option was groundwater control to install a French drain system and pipe and convey that water permanently to Kellogg, Idaho, about 13 miles away. And it's expensive to do things for forever. With adaptive management, however, we can look at the selected remedy for the SVNRT and take into account lessons learned from other projects and other new site information to help come up with a better, more viable solution to the problem. And I understand that it used to be that the rod was you have to go by the rod. The way to vary from that, going through a rod amendment, was too costly, too time consuming, and overall a lot of projects would follow the rod simply because it was the easier route to go. So with adaptive management, it's nice to be able to still work within the framework of the record of decision and use new information to find a better solution. The new repository that we are designing considerations and several criteria that it meets. It's close to the remediation sites. It has a large enough capacity for the expected contaminated materials in the watershed. It has existing access roads to the site. There are paved roads up on the left side of this photo. On the other side of this, the Lower Burke Canyon repository, which is this section here. And there is a there is clean soil and rock borrow source near this site. We are actually in the process of excavating about 340,000 cubic yards of borrow soil from this construction site. And the area was free of complex land ownership issues. The one landowner in this area was happy to sell the property to the Coeur d'Alene Trust, and the area is relatively flat, which allows for the contaminated materials to be stacked in a very stable configuration. So just as a, I guess, an update on some of the construction that we are doing, this photo on the left is the beginning of construction season this year. The photo on the right is a couple weeks old after they've salvaged about 3/4 of the soil that they are planning to move. Just a general construction oversight photo for you guys. The additional considerations that went into the design of this repository was the maximum waste volume after specifically the SVNRT waste gets placed into the repository, and we're expecting about 1.2 million cubic yards of available space after placement of the SVNRT. There's geologic faulting in the area. It's not an active fault, but it was something that we needed to consider. It's the Osborne Fault that runs just south of our new repository's design footprint. And this fault actually runs through the current SVNRT, which may be one of the reasons why that repository has failed. It's difficult to fully understand the complexities of groundwater flow through faulted areas. And in addition to that, and knowing that groundwater is difficult to fully understand, we wanted to try and identify the maximum high groundwater elevations through our site. So to do that, we installed several wells throughout the site, indicated with the little blue symbols there. And we determined how, I guess, the annual high groundwater level using the numerous wells and data loggers. We realized that it is important to have multiple years of groundwater data because our original salvage surface for soil put the base of the repository actually in the high groundwater zone, and we revised that during the 90% design. So we learned that groundwater elevation is highly variable, or we observed that it was highly variable in the mountainous regions that we're working in. In particular, I want to draw some attention to well 11 down here in the next slide. We had groundwater elevations in 2017 that swung 30 feet from the beginning of the year to the end of the year. And this red line indicates where our bore logs show current SVNRT waste. So our wells are showing that, like I said earlier, the groundwater is coming up into contact with the wastes at the SVNRT. So the data loggers were very vital to the investigation and to the design, because if you could imagine sampling this every couple weeks or even once a month, you could very easily sample on either side of your peak and miss it entirely. So the data logger has proved their value, being able to catch these peaks like they did. And we used the peak data around the site to establish a groundwater elevation over the multiple years. We picked the highest peak from each well, even if they didn't coincide in the exact same year. We would use the highest groundwater elevation and then to design the groundwater surface, and then we put the salvage surface just about 5 feet above that. One of the design features that we put into this in the area of the SVNRT repository after that gets removed is a clean fill, bringing the ground elevation up above that groundwater elevation and installing some additional base drainage system and some dewatering trenches in the area. So in general, we established that high groundwater elevation, and then we are installing dewatering trenches and general fill, just bringing our design surface up above the observed groundwater elevation. And the dewatering trenches that we have are, we have a detail there. They have general drain rock, like a 1/2 inch to a 6-inch rock or a 1 inch to a 6-inch rock, perforated pipe in the bottom of the trench, and the water will be, oops, sorry if that's loud for everybody. The water drains out to the perimeter of the site. This is the little video is a similar feature on a construction site in the next watershed over, just showing how much water one of these systems can collect from under your site. The video was taken near the beginning of the construction season, and water was flown out of that thing and could fill a 5-gallon bucket in pretty much a snap of a finger. It was coming out pretty quick through that area. So the base drainage system that we use on this site, I guess it's important to note that its intended use is not to be a leachate collection system. It's a separation layer from potential groundwater coming up or unobserved seeps sprouting up underneath the waste. So we placed our base drainage layer about 5 feet over the observed high groundwater elevation, and then we prepare our foundation. We don't necessarily want the foundation to be so solid that water cannot penetrate from above and infiltrate into the ground, but we want it to be solid enough that it's not going to slough and cause stability issues, if that makes sense. After the prepared foundation, we put down a 16-ounce non-woven geotextile, and inside of this drainage layer, so we have our designed surface here, geotextile, and then we dig our trenches in, our monitoring trenches, and these are filled with drain rock and a perforated pipe to observe if we have groundwater or water flowing in our base drainage system. So above this design surface, we have 2 feet of drainage rock and then another layer of 16-ounce non-woven geotextile. This photo was taken from the same 9-mile project as that dewatering trench video was taken. And we have our prepared foundation, geotextile, drainage layer, our additional layer of geotextile, and then waste being placed over a section of the drainage layer that has already been constructed. So in addition to these monitoring trenches, if we observe seeps in the surface of the soil salvage area, we will install seep collection trenches, which are just a little bit deeper than this secondary monitoring trench, but it has the perforated pipe at the bottom of the trench to collect the water from the seep and route that out to the perimeter channels of the repository. And one of the lessons learned that we took from the construction of this repository was the need for a lined ditch on the upper end of your base drainage layer for your interim in between your construction seasons. We had some erosional issues, and by lined I mean like an HDPE or LLDP, a plastic liner we want to collect the water and get it out from around the site and move it to the perimeter, and not allow that water to get into our drainage layer and get underneath the site. In addition, the repository was designed for phased construction, so we can be responsive to waste volumes. As construction continues, schedules change, project timelines vary, and we need to be able to be responsive to the waste volumes that are coming in. The base drainage system is going out in phases as well. We haven't collected soil from the entirety of the footprint and installed a base drainage system. We don't have unmanageable amounts of area open for erosion. So we are uncovering and constructing in the areas that we can use in a year or use in the next year. We don't fully open the site. And the phase design aspect to this project came in terms of the 2016-2017 data for groundwater elevation. We had time and schedule to continue working on the design, but instead paused the design waiting on some of that groundwater elevation information, specifically so we could have multiple years of data prior to establishing our soil salvage surface. So with this project, we've been able to come up with a very good solution to solve the needs inside of the Canyon Creek watershed. We can solve the issues with the SVNRT and respond with providing additional capacity for all of the Canyon Creek RAs that are coming into the that will be coming into the schedule here in the future. And we've seen some of the importance of pre-design investigation. Being able to understand your site prior to starting construction can be very important, because the cost of relocation can be pretty significant. I believe that if when they constructed the SVNRT, they were working on a limited budget and a very limited time, on a limited time frame. If you can put the time and money up front, it can save you money in the end. The groundwater fluctuation in the mountains can be very responsive to the spring snow melt, and that's one of the reasons that we have so many additional features in this design for water control. Some have called it internally the belt suspenders and duct tape approach. We really want to make sure we can control the water around these wastes to limit and prevent the future loading. And we can utilize lessons learned from previous projects and apply adaptive management during the design and construction in a way that we stay with broad coming, but we don't necessarily have to follow the exact selected remedy that was given. So I'd like to thank the trust for letting us work on these projects and develop some of these solutions to these interesting sites and locations. And I'd like to thank Cody Leckleitner and Todd Bragdon, which helped with some internal review and development of the presentation. And at this time, I will take questions if there are any. Did I lose anybody? Nope, I think I'm still sharing.
Cody, any design changes anticipated as a result of early construction observations?
Design changes, not so much yet. We have observed a couple of, let's see, where are the soil salvage photos? Nope. They are sooner. Not necessarily design changes, but you can see some seep. It looks a little bit wetter in this location. I'm not sure how well that shows, translates to the presentation, but this location we've observed groundwater coming out in our soil salvage surface. So we will be installing our seep collection systems as we continue on into the future. This area will not see waste this year. The base drainage layer will come in from this area, come across down through here, and then drop down and tie in down into this corner. So we will be monitoring where this water is moving around and collect that in the future with our seep collection systems.
Any other questions? Okay, well, I will say then, thank you very much, Cody. Great presentation. We will now be going on to another break. You can utilize this time to get some work done, or communicate with some of the presenters, or touch base with some of the other conference participants, and we will meet back here for another presentation at 3 o'clock.
Established in 1952, has been committed to analytical excellence ever since. We're committed to providing exceptional customer service experience with dedicated project managers available for assistance at any time, from the first contact with us through the final report being in your hand, and any questions you may have after that. We're a full-service analytical laboratory specializing in water, soils, and organic analysis, and now offering such specialties as radiochemistry analysis, aquatic toxicity, and PFAS/PFOA. We work with a broad range of partners in industries such as municipalities, drinking water and waste treatment, through mine exploration and reclamation, monitoring wells, stormwater, waste characterization, petroleum production and exploration, and with agencies from federal agencies to industry and manufacturing, all the way to individuals interested in their private well or garden soils, and working with clients all the way from Alaska to Mississippi. We provide sampling supplies and sample containers, preservatives, paperwork available for local pickup or shipped directly to your location. We provide convenient prepaid return shipping labels to get your samples back to us as effortlessly as possible. With 4 locations to serve you across Montana and Wyoming, give us a call today to set up your next project. More information can be found at energylab.com.
I'm Eric Mears. I'm with Haley & Aldrich. I'm the market segment leader for our mining practice. I've been in the mining industry or working with the mining industry now for about 25 years. We work for construction materials clients, we work for industrial minerals clients, and we also work for hard rock clients, which are the base and precious metals. Well, the material at this site ends up in a lot of different places, roads and highways and infrastructure and houses and sidewalks and schools. Materials that are mined here are really the building blocks of our society. And without sand and gravel mining, you don't have the modern society that we have today. We look for solutions that fix kind of the bigger picture. We're not just out there putting a hammer on a nail head. We're out there saying, okay, who are the stakeholders? What are the issues involved? What are the kind of interchangeable pieces here? Things that make a difference when you're trying to build a solution that meets multiple needs. We have our core practitioners, the people that have had their boots on the ground on mining sites, have often worked in the mining industry. We've got one profit and loss center, which doesn't silo our resources and our people. We don't compete against each other to solve our clients' problems. We can take diverse experience in different industries and apply them to deliver some innovative solutions for our mining clients. We ask a lot of questions. We ask questions about, okay, what are the things that are immediately right in front of us? What do we need to fix right now? Who are the stakeholders involved? What are the other pieces of the puzzle? The idea is that we come to the table once we've done a lot of listening with solutions that really fit our clients' needs.
Everywhere we're operating, we're the largest private employer there. People are engaged with the mines and they take ownership of the mines. And as a result, the company is committed to the community.
Before we begin, we think of the end. During the operation, how do we minimize our impact and protect the environment? And then ultimately, how do we restore and reclaim that land to other productive uses?
We have a responsibility to our workers that they can stay safe. We have a responsibility to the communities that the workers will return home for dinner at night. We have a responsibility to our shareholders. We have a responsibility to governments that we will make a profit and we will pay taxes in order to support the general infrastructure. We invest in the communities.
It's that we operate in the best jurisdictions in the world, in Mexico, Canada, and the United States. And today that's more important in a precious metals company than almost anything else in the world.
The company that has the right culture, they're going to do it responsibly all over the world. And in the United States, though, you have the best environment to do it the best, right? You've got great laws, you've got great workforce, you have great minerals.
We have a plan, we have the team, we have the skill set, we've got the operators. And when you operate well in a community, it shows in the happiness of the workers and the happiness of the community.
Instead of saying, that's not my job, you say, what can I do to help? So I'd rather it be done here where we can do it responsibly and you have a company like Hecla that does it, that cares, because we need these resources.
I'm Phil Baker, CEO of Hecla Mining, and we're responsible,
safe,
Responsible, safe, and innovative.
Mal Foster and Alongi is an integrated multidisciplinary firm consulting in environmental services, engineering, planning and development, GIS and data analysis, communications, and health and safety. We are passionate about working with clients to provide solutions for complicated sites throughout the Pacific Northwest. MFA has worked with the Coeur d'Alene Trust on remediation of the Bunker Hill Mining and Metallurgical Superfund site since 2010. MFA assists in program management and strategy, tracks documents and data, conducts site characterization and monitoring, and evaluates remedial action designs.
So I have it up on my screen.
Okay, did you share your screen?
Yes.
Okay, you've got to share it on Zoom.
Yep. Okay, let's try that. Share.
There you are.
Okay, cool. All right, here we go.
Okay.
Let's see, how come it's not, there we go. Okay, so yeah, glad to be here. Sorry we have to do it virtually this year. It'd been fun to see everyone in person, but hopefully next year. So my presentation is going to talk about my international forestry work that I've done with the Forest Service with a little bit of a mining twist. So our international program, the purpose of this program is to work together globally with other countries on forest management issues and biodiversity conservation. And so this program, many specialists throughout the Forest Service participate in this program for different reasons, whether the issues are mining or invasive species or forestry issues. The premise behind this program is that if we have healthy forests, it's important to have healthy forests globally to keep our forests healthy here in the United States. This work that we do in collaboration with the Department of State, United States Aid, Agency for International Development, the World Bank, and other governmental and non-governmental organizations. So I just thought I'd share with the group 3 of the trips that I've done over my career. And the first trip was to Venezuela. And so we arrived in Caracas, and it's kind of interesting when you go on these international assignments because you always land in a nice city and get a nice hotel, and then you kind of go from there. So we landed in Caracas, and from there we flew to a small town called El Cayal to the mining company. You can see the name of it, CVG Minervan. And this was basically, it was a pseudo-governmental mining company for Venezuela. So you can see the main office in the picture and the geology truck. So the purpose of our trip there was to review, we were asked to come in and review 2 cyanide plants and 1 cyanide facility, tailing storage facility. So they were having problems. You can see here that the first one that we looked at, this Peru plant, the totally uncontained cyanide tailings. They just let them go into the environment, into a drainage ditch. You can see a small community in the background, and we just happened to be there when the kids were heading to school. You can see the children walking across the cyanide tails, going down over the bank and crossing the live cyanide tails, the gray on the bottom left. I was shocked. And then this is a picture of the plant with the cyanide tails. They would come out of a pipe and go into a concrete lined ditch. So this was their delivery system to the disposal area. You can also see in this photo the black plastic barrels that were feeding in other chemicals to the site. So some of the things we did is we went throughout the area and we looked at how are you running this operation, and this is their cyanide storage area. Again, we walk up to this building, you can see barrels on the side, you can see the condition of some of the barrels, not quite up to the standards I was used to. And then, you know, one of the things they said is we'd like to cut costs, and so we talked to them about their cyanide usage and what percentage they were using and so forth. And so we asked them if we could see how they were adding the cyanide into these plants. And they took us to this area right here, and they said, yeah, this is where we add the cyanide, but it's a holiday, so nobody's working today, so they just turned a couple of barrels up on end and did a mass addition of cyanide, and then went on holiday. So we thought that probably wasn't the most efficient way to keep your levels at a constant percentage. This is the tailings storage facility that they took us to. You can see the pump on the left on a pontoon. Here we had a little bit of a talk with them about freeboard. It was a concept they hadn't thought about, keeping the level of that water down below the dam, so that we are actually standing on the dam. In this next picture, you can see where they've had a blowout of the dam, and they've fixed it. So they were having releases from this facility, again, very high cyanide levels of water. And here you can see this was higher up in the tailings pond area. The people are actually using this water. They're doing their laundry, the kids are swimming, so that it's being used by the folks. And then this is what we found when we went to the bottom of the tailings dam. The tailings dam was about 200 to 300 feet high. It was quite high. Again, there had been releases into the river, and we asked to go to the bottom to take a look up, and we found lots of folks doing the artisanal mining and using their pans to look for gold. Also very heavy mercury use. And so basically, as we did our work, we had a translator with us. We would ask questions and get the information translated back to us. And basically, I guess you won't be surprised at our conclusions. Again, this was 1996. We had three major conclusions. We said, you need to minimize the cyanide use in your mills. They had too much cyanide. They weren't able to have it degrade before they released it to the environment. Plus, it was costing them money in using the cyanide. The other thing we did was talk to them about ideas on enhancing the natural degradation of cyanide, how they could take those solutions as they came out of the mill and reuse the cyanide or get it to degrade in the sunlight. And then lastly, we just encouraged them that to treat their cyanide tails before they released them into the rivers and the environment where children were walking to school and elsewhere. And they were interested in this, but it always came down to money. The other thing that was interesting here was that they really didn't have access to technology and publications and information. We worked with a mining engineer over there who had mining engineering magazines that were just tattered. He had read them so much. One of the things that I'm standing here with, many might know Jeff Gabarty. When we got home, we boxed up all our old publications and mailed them to them. They were just starved for information. So, so that was our Venezuela trip, again, with 3 different cyanide processing facilities. The next trip that I took was to the Republic of Georgia in 2016. So we flew into Tbilisi, which is the capital of Georgia, just a beautiful city. Unbelievable, the old and the new. You can see the bridges and the different buildings and structures and some of the old churches. Also had quite many hot springs baths in this town. So here I traveled with Ruth Seeger to Tbilisi, And our main task was working at the Ministry of Environment and Natural Resources and giving a week-long workshop. So this group was tasked with regulating the mining industry. They had several laws on the books, but in general, the mining companies operated, and there was little to no oversight or administration or permitting. The only real permitting in place was the licensing of the mines, which was giving them the rights to develop the minerals and have the rights to the minerals. A lot of, and we'll see pictures, a lot of what we saw was, it wasn't long before that Georgia had been part of Russia. And so there was still the Soviet influence at the mining operations. So again, this workshop, we presented, you can see the folks sitting in the conference room. We presented to them how we regulate mines, how we do environmental assessments, what we look for at mining companies, what kind of information we ask for in plans of operations to work with the mining company to come up with the best operation and address environmental concerns. You can see in the upper left, this is Georgian. It seemed like there were 10 words for every one of our words. We had 2 translators. Language was definitely a barrier on this assignment. It was difficult. A handful of the young people did speak some English, but in general, they did not speak English. So again, we taught for 3 days, and then we did do a field trip. So one of the emphasis of our training was to teach the folks how to get information from a mining company, a plan of operations, what is the mining company going to do, and then to assess, some ideas on environmental mitigation and to make the operation better for the environment. So in the course of that, we took this group to the field, and we went to this Sadarsky mine. It's a gold mine, cyanide heap leach. You can see, you can see how the cyanide heap leach is being constructed. It was quite haphazard from my perspective, in that there would be operating areas and then new liner laid down and more. You can see it's quite active with liners and adding more material. This is a view looking down to the processing plant area. You can see along the bottom of the heap, there really isn't a berm or a channel of any sorts. It's just kind of build it, get some cyanide on it, and build some more. Quite steep, a lot of water coming into the facility from outside, adding to probably the inefficiencies of processing the gold. Once again, we spoke with folks about freeboard. Somehow they like to fill up their ponds, and there tends to be releases into the environment. I thought this was interesting, the many return lines coming in from the cyanide heap leach, just lots of cuts through the liner to provide for these lines to get to the mill site, and a lot to monitor. This is after the mining visit. Of course, when you're in another country, sharing their food is a big part of what folks want to do with you, is give you a nice meal. On the upper left-hand side, the 2 fellows on the left are with the mining company, and they were our hosts, and then myself, Ruth, and folks from the ministry. As we left the site, You can see I've pointed out the tailings impoundment above these housing units, these apartment houses. There were many mines that we were not allowed to access. We tried to access different areas, and they weren't willing to let us come visit. So we were fortunate to get to go to one mine. This is just kind of showing the people, you know, when we go on these assignments, we get to have some fun, interact with the local folks. In this instance, we went to the countryside and visited an orphanage that three Georgians had started when they were 19. They started an orphanage and they've been running it ever since. It was very impressive. And then just one last shot showing you Tbilisi in the daytime, and then at night with the castle on the top of the hill, a modern tram going up the side. It was just a lovely city, very, very safe and fun to walk around at night. So the third trip that I was able to experience was to Zimbabwe, Africa. Never dreamed I'd see something like this. So this one was also a workshop where we taught for 2 days, but we also had presentations from many of the local organizations. They don't really call them NGOs like we do. They call them civil society organizations who are interested in protecting the people or biodiversity of the animals, that type of thing. We also had mining personnel from the government who presented what their rules and regulations were and how things worked. So it was really a sharing of information amongst us to work towards solving problems together. We went out and visited the Matuko granite mine. You can see the mine in the background. Basically, it's a quarry. And then the locals in the foreground with their animals. People the mine sites I've visited in these countries are very different in that people live right in amongst the mining. It's very different. They're not excluded. Sometimes they're removed to make way for the mining, but you can see their safety sign for the blasting. And then this is just an example of a abandoned pit with some water in it, and then the end product. They put a number on every granite block and track their product that way. One of the problems that the local community had was children drowning in these little lakes that formed. An issue that we dealt with in the field was this road washout. We went to visit this community, and they came out. The whole community came out to visit us. They knew we were coming, and they were there waiting for us. The issue was that the mining company had caused the washout of the road, and they weren't willing to fix the road, causing this community to have to travel 20 or more kilometers out of their way to get to market. And it was a real problem for them, and they were trying to get resolution. While we were in Zimbabwe, we had the opportunity of going to meet the people who do this anti-poaching tracking specialist project, where they actually hire local young men, you can see in the left, who track the rhinos and the elephants and keep them safe from poachers. This contact was made by the lady in charge of international forestry. It was part of her other conservation work. And we were lucky enough to get to go and spend the weekend with these folks. You can see the little 2-year-old who caught a snake and was quite proud of it. Some of the animals we saw, it was, again, I never dreamed I'd do this, but these folks live out there. They took us in for the weekend and took us out on in their Jeep to look for animals, and we really saw them all. So it was a great time in that regard. Now, here's the last trip that didn't happen. We were supposed to go to Liberia, Guinea, and the Ivory Coast in February of 2020. That trip didn't happen. We had plane tickets, we were packed, the whole bit. We really don't know what happened, but Liberia was not willing to give us visas to come into the country. I do wonder if they knew COVID was coming, or if it was something political. But we could not get visas, so we did not go on this trip. We participated virtually. But I did want to show you, I found this pretty interesting, that the Mount Nimbin mine actually mined the highest peak in West Africa. This peak, the 3 countries listed below come together at this peak. And so this highest peak used to actually be higher, but it was mined by the iron ore company. So it's a very large iron deposit in that country, very high reserves. Much of the reserves are in areas of nature preserves where they're preserving for chimpanzees and other things. And so there was some conflict between the mine and the environment considerations. And that was part of the issues that we were going to be working on. So let's see, lessons learned. You know, every time I came home from these international trips, I really felt like I was a changed person that really opened my eyes to a lot of things. And, you know, it made me feel so fortunate to be in the United States, where we do care about the environment, and we as the mining industry do a great job taking care of the environment. And these countries, these people just struggle to survive. And they do care about their environment because it's their livelihood. The food is their livelihood, the animals are their livelihood. And many times, like I said, many of the impacts are often civil society issues, such as people being displaced because of mining. Literally, people have lived on the land for hundreds of years, their villages being moved so that a mine can come in. Or, for instance, what we saw where the road was taken up by the mining company and not repaired, or water well issues. So, you know, often I would come home and what I would realize is that what's important to these people, and, you know, when you think about it for yourself, what's important is food, family, and friends. And I met a lot of great people, and again, just realized you don't have to have a lot to be happy. Just food, family, and friends. And so with that, you know, I'm thankful you're all my friends, and I'll take any questions you might have. Uh-oh.
Any questions for Mary Beth? That was some awesome locations that you traveled to, Mary Beth.
Thanks.
Okay. No one has any questions? All righty. So thank you very much, Mary Beth. That was extremely interesting. You've gone all over the world.
Yeah.
All righty. So our final presentation of the day is from a gentleman named J.P. Jutras. He is with Jade Leader Corporation. JP is a professional mineral exploration geologist with some 30 years of experience in the mineral exploration industry. He has worked in over 15 countries on 4 continents with numerous public companies, including Placer Dome, Prism Resources, Golden Star Resources, and now Jade Leader Corporation. During a stint in China, the scale of the changes in the jade industry became obvious, and a 1-month initial research journey to some of the major jade carving centers and markets in China was undertaken. This led to the creation of Jade Leader Corporation as it entered the international jade space and began taking steps to establish itself as a leader in jade exploration. So I will turn the controls over to JP, and welcome aboard.
Thank you. Can you hear me?
Yes.
Excellent. I'll share the screen now. All right, well, thank you for the invitation. I was told there's only very few exploration stories here and people are looking for something different, so I hope we'll fit the bill as I make the case for jade as a potential new commodity for the United States. We are a public company, so I have to give you the disclaimer, which is consideration of anything always comes with market risk, geology risk, permitting risk, title risk, and now the bug, of course. So please review all disclosure on our website. I am the qualified person for the company under National Instrument Policy 43101. So I check all the technical disclosure and we're responsible for it. A little presentation, Pat. This is going to be a 10,000-foot view. There's lots to cover. I'm really here to give a lot of background. So I'll just reiterate a few things about myself and what my awakening was. Then what the general market space is for jade itself, and then the advances that we've had and the successes we've had in exploring in the States for jade itself. So you've heard it now. Participated in major discoveries in the metal space really since working in 1988. Latest big project was a 1 billion ton plus porphyry deposit in Mexico, which was taken over by a major mining company. So we're quite familiar with the risks of the exploration space as well as the potential rewards. Now the mineral exploration space it's always complicated, but it was a little simple because of two things. First, you have published commodity prices. So gold is worth this much, copper is worth this much. And then you have baselines, which is if you're looking for open pit, these are just guidelines that we use in exploration. You got to start at 10 bucks a ton of ore value. If you want to go underground, you need at least 100 bucks a ton of ore value. And then all the other pieces come into that. So good parameters to work with in the field. Now, I was also doing something else on the side. And I'm just going to go from 89, where I was making jade jewelry to sell at university to pay for my beer, through a bit of my carving evolution over the years with different materials. And one of my awakenings here was that when I bought most of my rough jade was in the early 90s, and it was about 5 to 10 bucks a pound for the material. I had to start buying jade again in 2015 because I was running out of material, and what I was buying for $5 to $10 a pound was now selling for $200 a pound if you could find it. And that was fairly low-end material. So I didn't understand what happened, obviously big change. But during that period, I was also invited by my carving teacher from 1996 to go and compete in China at one of their largest annual jade carving competitions. That started to provide me the answer as to why the prices had gone up. It was a big awakening. It was actually shocking. I thought I was going to the Lander Rock Show and there was a little competition, but the Zigong Bay Jade Expedition that year had over 90,000 visitors over 2 days. It was in 2016. There were over 515 competing artists, 25 of which were international artists and the rest were Chinese. And I just got to see what they were doing and the amount of interest that was there, and it was absolutely mind-blowing. From there, kind of started looking at what was happening in China with regards to jade. Here we're talking about nephrite jade. I'll touch on jadeite a bit later. So some of the jade prices, and these were not markets where you expect to pay 10% of the price if you haggle a lot. These were very established, well-established, serious companies providing good rough to the master carvers. So a rock like this, which is about £1.5 pounds, was $115,000. Might get 10% off. A little darker material, $2,900 for that rock. The pendants they carve out of those things will typically go from $60,000 to $100,000 each. And I was, you know, from my little Canadian carving and earring days, I was just blown away. I got to have a chance to sit down with one of the master carvers, probably one of the better ones in China, or the most recognized ones. And I told him, well, I think I'm going to go look for jade. What should I look for? And he actually opened the vault and showed me a bunch of material, because I told him, says, essentially, if I'm in the exploration business, I'm working for you, what should I go look for? And how much is it worth? So he pulled out some nice greens from Russia, you know, lower end material, and told me the evolution of the prices, 2013 to 2016. So these are pieces that he had bought himself. We're looking at $240 to $300 a pound. As soon as we get into the whites, this was Russian material, about 5,400 a pound. But the higher end and really Chinese, what they call the mutton fat, which is a special shade of white, really, will go for $55,000 a pound. Now, I was a mineral exploration guy looking for rocks worth $10 a ton. So I wanted to learn more about this. And I wanted to understand if this was a bubble or a fad or something. Who knows? Now, imagine a gemstone that for 2,000 years was only known in legends in China. Before China was consolidated, the emperors would bury the emperors and the families in jade suits. And these things had stayed as the stuff of legends or the collective consciousness for over 2,000 years. Nobody had seen one until they found the first ones again during his excavations in the 1960s. They found over more than 10 now. This is more than a dingle and breakfast at Tiffany's and 3 months of salary. I was really struck by the depth of the relationship between jade and the culture. In the lower one, this is a sarcophagus. It was about 2,000 jade plaques, 1,700 gold wires holding it together. There's a Smithsonian Channel YouTube video. It's linked on our website at jadeleader.ca. We have a resource page. And what they mention here is that when they found this tomb in the late 90s, the only thing left in the tomb was the jade. Everything else had been looted 2,000 years ago. The bronzes, the porcelains, the scrolls, everything was gone except the jade. And they speculate that nobody could steal the jade because it was imperial property, and if you couldn't fence it, it was too precious to steal. Now that's part of the history, and of course we go on for a long time here, but it's not only in the past. 2,000-year tradition of the Olympics, the best person in the world gets gold. Around 2008 in Beijing, for the first time since the inception of the Olympics, the medals were changed to reflect the Chinese event. And if you're the best in the world in China, you get white jade. So the medals were gold, silver, and bronze on one side, and they were jade of different colors on the other side. Didn't seem like a fad to me. Got to sit down with some people, talk about it, get some numbers, condense them here. The estimate for the jade market in China, nephrite, that's not including retail, was $30 billion a year. We had that from a seminar talk from one of the major economists and confirmed as well with Master Chu. Jade Life, a book published by Andrew Shaw, who's one of our advisors, was published in 2018, mentions it again. Feeds a huge industry. In 2016, when I got my numbers, out of 5 major cities, Suzhou, Yangzhou, Jianping, Yeyang, and Siwei, they estimated at 255,000 to 270,000 jade carvers. Small space, we don't have a lot of numbers. The last time anything reliable was published was by the GIA in 2015. At the time it was quoted Canada was producing about 400 tons a year, China about 40 tons a year, Russia 100 to 500 tons a year. Canada's production went up later in 2016-17, hit about 1,000 to 1,200 tons a year. Canada has been a big producer for a long time. There's a couple new countries, Indonesia, Afghanistan, Yemen, small-scale production. It's all mom and pop and artisanal stuff. The big one has been Burma or Myanmar, 20,000 tons a year, all jadeite, with a trade estimate value between 10 to $30 billion a year just for the rough. To make it comparable to an industry that we know, which would be the diamond industry, look at global sales of polished diamonds and global sales of rough diamonds, periods 2006, 2013, here 2010 to 2017 estimated. You know, global international rough diamond sales orbit between 12 and 16 billion dollars a year, not this year, of course. And then the polished goods before they go to jewelry, 13 to 23 billion a year. Much smaller in scale than the jade industry, about which we know nothing. So I was really quite intrigued. Potential for growth. The diamond guys are really trying to get into the Asian markets. They spend a lot of money marketing stuff there to make them buy diamonds. And they compile a lot of fun data. And that was the projection of the growth in the middle class in China in red, going to 2030. And then India as well. Except, you know, these people don't buy diamonds. They buy jade. So I was getting a little excited. I needed to understand why that was happening. So I looked at some really base indicators as to why the growth is happening now. It's a perfect storm of factors, really. Sorry, I'm just moving something around on my screen here. This is a 7,000-year-old market, and it's only been in an abnormal hiatus since the fall of the Qing dynasty in 1912. So it's a return to affluence by a Chinese market. Population's gone up. And now they have money. There's the GDP. I mean, X kind of marks the spot. They're back in the market. And they also trained a new generation of jade carvers, hundreds of thousands strong. They require material. So this is a good commodity space. China's not the only one, of course. It's most of the Asian diaspora. You look at Hong Kong, same kind of GDP growth. Singapore, same kind of GDP growth. Taiwan, except the chart's a little shorter in time. Interestingly, Taiwan was reportedly a fairly big buyer of Wyoming jade in mid last century, so 50s and 60s. You know, that was kind of all the stuff that got together and was exciting me as a market opportunity. But what I wanted to see was evidence. I want physical evidence of this. Very difficult, small mines, all private, most of them artisanal. So I asked friends in China, said, okay, can you send me some evidence of a more robust exploitation of the material and who's feeding this market? The first one was in Hotian, which is in Xinjiang province in China. Historical source of jade for thousands of years, typically collected by naked women, and the idea was that they were yin in nature, female in nature, so they would walk along the river, and when they connected with jade, which was a masculine stone, yang, then they could recognize it and collect it. Now, how times have changed, because as soon as the price went up, the abomination happened, and they threw all the equipment they could at it, and essentially, you know, probably sterilized a source in a few years that had supplied thousands of years of material. The other one is in Burma. I'm sure some of you have read about it or heard about it. There's been a big landslide there last month, killed a few hundred people. And I kind of did an eye in the sky analysis. I mean, this is a source that's been producing jadeite since the mid 1700s. Jadeite first got to China in 1780. And even up to 2010, when you go on Google Earth and look at satellite imagery, there's not even a road to bring a truck in there. It's really artisanal and surface workings. By 2018, the footprint of the operation was about 10 miles by 2.5 miles. And in 2015, the heavy equipment started to arrive on an extreme scale and velocity. And this is kind of what it looks like. There's no published prices, but when I see people spending this much money to get something, they must want it. This is inside the footprint of the operation. It's huge. It's really big. It's the only known supergiant in terms of production. And at velocity at which they're attacking it, I mean, who knows how long it'll last. And it's led to the conclusion that more jade has been mined and delivered to the market in the last 15 years than in the last 7,000 years, because everything's gone mechanized at a huge scale. There are two types of jade, nephrite and jadeite. They're both unique in being the toughest mineral aggregates known in nature, not the hardest, but the toughest, which is why it can be so intricately carved. Nephrite is a traditional historical jade of China. It's an amphibole. It's really the tremolite actinolite series, a calcium, magnesium, iron silicate, which is hydrated. It's pretty dense. Color can range black to white, most often found green, blues, yellows, and reds. The bigger producers today, Canada, Russia, and US, and China, sorry. Whereas jadeite, the major producer, is the one we've just seen, although there's some production coming out of Guatemala now. First introduced in China around 1784, but it was also the stone of the Mayans, the Olmecs, and the Aztecs rulers in Mesopotamia. That one's a pyroxene. I'm not going to touch on it more because it's not what we do. Factors affecting price, quality. It's a bit like the 4 C's of the diamond world, you know, color, clarity, cut, and carat weight. Again, color, translucency is very important, size of the piece. As soon as you can make a bangle out of a piece of jade, which is the bracelet, the round bracelet, price goes up exponentially because the market's so big for those things. The workability, you have to be able to work it, so no flaws, no fractures. Pedigree and interpretation, of course, add to the price. If they're antique jades, they'll always be worth more. Now, taking all of that in consideration, we decided to go and look for jade. So our current exploration portfolio in Washington, we have 1 project, 18 lode mineral claims, about 360 acres. In Wyoming, we have 5 projects, 99 lode mineral claims, and 1,980 acres. We'll just give you a quick overview of what we've been finding there. Now, nephrite's a special beast. I mentioned it's an amphibole, it's tremolite, but tremolite that grows with parallel fibers can be picked apart with your fingers. It's a very brittle stone because it's just long fibers. Think of a stack of wood all lined up side to side. You push the pile, it falls apart. In order for it to be considered nephrite, the fibers have to be intergrown or felted, which we see here in a micrograph. So to really stacking the wood crosswise if you want, and that's what gives it the toughness that allows it to be carved to be so durable. So it's not just looking for a mineral, it's going to be a mineral that grows in a certain setting, which is not documented. There are no models for this. We have to develop our own. We started in Washington, hand trenched. There's a vein of nephrite jades, about 3.5 feet. Serpentines on one side, they're the magnesium source, and calcsilicates, they're the calcium source, and we have this metamorphic metasomatic mineral in the middle, which is actually quite nice in appearance. There's some gemmy material, much less inclusions, much less spots, more uniform color, and some really interesting cat's eye or chatoyant jade. That one we mapped, and then we actually went ahead and drilled the same way we do any kind of exploration, mineral exploration project. Trench we just had a picture of, there's the lens of jade, went through it in 2 spots, and then went sideways a couple directions, moved over. So we drilled this thing for about 120 feet of strike length. And there's a cross section, there's the initial trench, going down here, there's a fault offset, and it moves down this way. Again, the geology, we have the calcsilicates on one side, the serpentinites on another side, and the lens itself that we've intersected in 7 spots is anywhere from about 3 feet to 15 feet in thickness. There's some of the pictures of the core, various types of material. We're very happy to be able to demonstrate that these things can have continuity because it had not been documented. Again, some of the various qualities from that project, very nice chatoyant, cat's eye one, blue-green, gemmy color quality. And these are more modeled so to be considered carving grade jades. This is very similar to Canadian material that dominates the market coming out of North America. Now, the chatoyant is also color change. We go from a forest green to a seafoam blue. Very interesting. Anybody who's in the gemstone market knows that these things are properly marketed, you have enough of them, they can command a fairly substantial price. So we like the material. Now, Wyoming historically has been a producer. It's had various green gold rushes from the 30s all the way to the 80s. And there's even things like the Kraft window. North Shore Baptist Church, Chicago, is called the Kraft window because Mr. Kraft, the founder of Kraft Foods, was a big jade collector, and he loved Wyoming jade, so he had this done. Great carvers. The Sunberg Jade Carving Facility from the 60s and 70s at one point had up to 50,000 customers a year, 20 people working in the shop, 100 tons of jade in inventory, exporting to Asia, which was at the time Taiwan mostly, and Europe. So there have been times where there was a bit of a jade culture and a bit of a jade market in Wyoming. Now, most of the collection that was done in those days was at surface. It was mostly considered to be alluvial deposits, and the sources remained elusive. And when the surface material ran out, essentially the supply ran out and things died out. We got involved in there thinking it had to come from somewhere. So 2018 to 2019, we acquired 5 projects, most of them by staking. Found a number of jade outcrops, mapped out the geology. We did airborne surveys to see if we could track these things through remote sensing as well, and there's evidence that we can. And then we'd tested enough jades of various qualities to say, yeah, it's worth trying to see if we can put something together here. In September, October 2020, we picked some of our best targets, permitted trenching, and went in with a dozer. So got success in 2 trenches. In about 3 weeks, we collected 23.5 tons of jade. Their shape is interesting because these are actually xenoliths of mafic rocks that were recrystallized inside a large hot hydrothermal breccia. But all of this material here comes out of this single trench, and we're cutting across the system as well. So after the program, we took some samples home to check the quality and stored the rest in containers over the winter. And the stone testing that we did, so most of the trenching material is quite mottled. The idea is also to see how thin you can cut it, so you can see how competent it is. So can you carve vases? Could you make tiles? Could you make tabletops that'll be backlit? Are there architectural uses for it? And then some of the other material was the more gemmy material for international markets and for jewelry. So very consistent color and fine texture. We've gone back. I just come back from the field now. We had 2 objectives. First is test larger scales of these materials to see what the potential is for carving markets and architectural use. We'll continue doing that. And also look for the source of these materials, these more gemmy materials. Now, historically in Wyoming, all the best quality stones, finer texture, better grain, more consistent colors, have been found at surface, as I mentioned earlier, as what they called ventifacts or slicks. And the theory was that these were just the harder parts of the mottled jade, but the mottled jade had eroded away, and you'd kept the gemmy parts because they were more resistant. And our research work was suggesting there might be something else going on. So last July, when I went to the field, we said, okay, can we find an actual system of this material? And we did. So this one we identified, it's on the hanging wall of a pegmatite dike that's vertical. We mapped it over about 50 some feet of length. And over a couple of days, we recovered about 110 pounds of very, very fine grain jade that we will be test marketing, see what the market acceptance and potential value is. So kind of breaking ground and identifying what the systems look like. This is kind of the update, and don't want to go over time. There's my summary. So since 2018, we built and successfully tested proprietary geological exploration models for jade. Acquired 6 properties, all of which have confirmed jade occurrences right now at various stages of testing. Continuity of geological potential for scale by drilling and trenching, we've shown that. And now we're entering materials preparation and marketing stage to generate information on potential economics of these discoveries. Well, that's us. We trade on the Vancouver Stock Exchange as TSXV, as the symbol is jade, over-the-counter VB market, in the States, MCKRF. Thank you so much for your time. Want to leave time for questions. Anybody wants to get a hold of me directly, jp@gold.ca. And there we are. Any questions?
So you do have a question. How do you deal with mining potential ACM? It seems that it wouldn't be profitable.
It really depends what kind of prices one will be able to get for the materials. I mean, essentially, we wouldn't look at this in the same way as a a gold project or a copper project. It would be looked at mostly like an industrials mineral type project. So you can have, at some point, if there's market acceptance of the material and there's desire for it to enter the market, then we'll have to do larger bulk samples and just calculate a value per ton, which will not be the material, but the host and the material. And then we'll be able to assess economics.
Okay. Any more questions? I see where, did some previous questions come in for Mary Beth earlier?
Yeah, they came in during his presentation.
Okay, so any questions for Mary Beth, you can contact Mary Beth directly, but any more questions for JP? That was a very interesting presentation and unlike anything we have ever heard of before. So I'm.
Well, thanks for the invitation. I was told if
Yes.
people are looking for something different, this is as different as it
Yes.
gets.
Yeah, it was I found it very interesting. I appreciate it and I appreciate your time. So, okay, and we also have another question. Are your claims on public or private land?
All of the claims in Wyoming are on BLM, on public land. The claims in Washington are BLM administered, but they're its National Forest Service. And one of the things I have to say, just on that topic, working with the authorities so far in terms of permitting and things like that has been really wonderful. And I think one of the reasons for that is because we're looking at things that have such small footprints. And really at the end of the day, it'd be a quarrying type operation that, it doesn't raise the specter that, oh my God, if we let them explore, there's going to be a tailings pond and there's going to be all sorts of other problems. So there's been a lot of support in helping us through the process so far.
That's wonderful.
It is.
Here's a question for you. Who would you be selling to? For instance, wholesalers or end users?
There are not really wholesalers. There are carving factories. There's some in Thailand, Taiwan, obviously China, India is doing some jade cutting as well. Because of the skill set that we have, I mean, most of the people that I work with, the contractors that work with us, everybody is a jade carver with at least 30 years experience. So we're not stuck with a pile of rocks that we have to find somebody to take off our hands. We can actually start exploring, okay, can we take some of this material to market and actually capture some of the upper ranges of value as well? So I don't have an answer to that question. All I can say is that we're going to look at anything that makes sense to start creating value here. We've got the material. We know there's lots left in the ground. If we can start moving some of this, we can put some economics together. And I see quite a bit of potential in the US, personally, as a market. I mean, it did have a vibrant market in Wyoming in the 70s. Went away because people thought it was gone. But especially now, a lot of the American money is not going to Switzerland, or it's not going to Spain and Italy on vacation. I mean, when I was there in July, it was busy. And there's a lot of tourism. There's a lot of people, hey, we're working at the backyard of a hotel cleaning and polishing stones. And people are going like, where do we buy this? So we're actually quite excited about making products specific for the US, see if the cost base works, see if the market acceptance is there, and actually try to open that market up.
Excellent. Another question, are you looking for jade in California?
We're not, and there's two reasons for that, two main reasons. Actually, there are three. Quality-wise, the California deposits are better known than Washington or Wyoming. And the distribution of quality is not something that I find extremely attractive. I mean, if you look at diamond deposits today and who's struggling and who's not, the only people that will make it through this round of depressed prices for a year, 2 years, however long it's going to be, are the people that have the top end stones, because those always move. So if you don't have an indication that you're going to have some of the higher grade material in substantial amounts, it's difficult to get involved in a project like this. Second, I think California, from a permitting point of view, might be a lot more difficult to work in than many other areas. And third, there's actually a fairly vibrant local kind of small scale carver prospector type people that have their own claims and they're doing their own thing, and there's no reason for us to come in there and disrupt that.
Okay. Wonderful. A lot of great questions for JP. Anyone else?
I hope there's more. We don't get a lot of conferences these days, so I'm happy to tell the story and answer questions.
Well, that's great. That's great. Yeah. Anyone else?
I appreciate you.
Okay, well, I think that's probably going to wrap us up as far as presentations go for today. Thank you very much, JP, for closing out the day for us. So we are going to have our 1 hour Zoom happy hour. So for those of you that are staying on, please turn on your microphones. You can chat with one another. You can also go on and privately chat with one another. If you can send a private chat to other participants that are on. So utilize this time to get in touch with one another and answer or ask any more questions that you have regarding presentations. And we will see you back here tomorrow morning at 9 a.m.
Hey, Dirk.
Well, am I the only person here with a classic American Pilsner on tap?
Who is this? I can't see.
Hey, Gunnar, you probably are.
And that's the beauty of the basement office. The keg is about 20 feet away from me.
Life is good.
Well,
This is Jim Gusick. I'm wondering if you'd rather have a bottle in front of me than a frontal lobotomy. Is that?
Much rather.
Well, I'm still in the office, so unfortunately, I'm just going to have to dream until I get home.
Don't work too hard, Jim.
Oh, I know. I'm currently, I've got a lot of different things going on, Wayne. It's as a matter of fact, I see Eric's.
Yeah, I said don't work too hard.
Yeah, all right. You and I need to chat about birthday.
Okay.
Before you, maybe we can do that offline, and share thoughts, because we got some data back from them, and I'm going to be talking about it on Thursday.
Cool.
Yeah.
Well, I've got MSHA tomorrow, so I won't be on tomorrow.
Okay. Well, maybe we could. Why don't we just drop off of this and come back?
Yeah.
Just
Sounds good.
drop off of this call, and I'll Zoom you. I'll send you a Zoom request, and we can chat.
All right. We'll talk soon.
See ya.